لو كان واحد ضمن
يا سي شرمان السلام عليكم.
بسم الله. تسمع؟ بسم الله الرحمن الرحيم. Good morning, ladies and gentlemen. I am Dr. Lazhar Mohandi from University of Qasdi Mirbah, Wargla. Allow me to extend a warm welcome to Rector of University Vice Rectors, Dean of Faculties, and Directors of Institutions, all participants in this conference, lecturers, students, and assistants. Now, I'm going to present presentation on the first conference on sustainable energy and advanced materials. This presentation is divided to 3 parts. Introduce our university, our faculty, and first international conference on sustainable energy and advanced materials. In this section, we are going to talk about the objective and topics of this conference. I'd like to give you some information about our university. It is located in the southeast of Algeria, in Ouargla city. It is composed from 10 faculties and 2 institutions distributed in 3 poles. Number of students is more than 30,000 students. These 2 pictures show the rectorate of our university. I'd now like to move on the next part, Faculty of Mathematics and Matter Sciences. The first established faculty in the university is the Faculty of Mathematics and Matter Sciences. The left picture shows the library of our faculty. The right picture shows the entrance of our faculty. In this table, there are some information about our faculty. Location is in the first pole. We have 3 departments: Department of Physics, Department of Chemistry, and Department of Mathematics. The number of students is 2,100 students. The number of lectures is 105. We have 6 research laboratories in our faculty. Let's now turn to the first conference on sustainable energy and advanced material. As objective, the first international conference on sustainable energy and advanced materials provides a forum for students, research, and practitioners from industry around the world to present papers and to exchange ideas on recent developments in sustainable energy and materials science field. This conference will include virtual contributions by invited speakers, oral presentations, and poster sessions. This event also offers space for companies to present their innovative products and services. In this table, we have topics of this conference. This table shows advanced materials topics. We have 12 topics. The first column topics, we have submitted communications, accepted oral communications, accepted poster communications, and rejected communication. The topics of advanced materials are optical and laser materials, electronic and magnetic materials, semiconductor and supraconductor materials, nanotechnology and nanomaterials, computational materials science, graphene and 2D materials, piezoelectric materials, materials and sustainable chemistry, smart and intelligent materials, photovoltaic materials, radiation and matter interactions, plasma, physics and modeling. This is for advanced materials topics. For sustainable energy topics, we have 12 topics. These topics are solar thermal energy, solar photovoltaic technology, wind energy, geothermal energy, biomass energy, hydrogen energy, and fuel cell. Hydropower, electric power systems and control, energy distributions and storage, building energy efficient and materials, hybrid and integrated energy system. Energy modeling and optimization. For other topics, we have artificial intelligence and smart power grids, climate change, physics theory and simulations, astronomy and astrophysics, nuclear energy and technology. We can summarize these topics. For topics of advanced material, we have 12 topics. Submitted communication, we have 678. Accepted oral communication, we have 164. Accepted poster communication, we have 299. Rejected communication, we have 215. For sustainable energy topics, we have 12 topics. Submitted communication, we have 262. Accepted oral communication, we have 101. Accepted poster communication, we have 116. Rejected communication, we have 45. For other topics, we have 5 topics. Submitted communication, we have 110. Accepted oral communication, we have 28. Accepted poster communication, we have 52. Rejected communication, we have 30. The number of all topics is 29. Submitted communication, the total of submitted communications is 1,050. Accepted oral communication, we have 293. Accepted poster communication, we have 467. Rejected communications, we have 290. For invited speakers, we have 7 invited speakers. Accepted communication, we have 60. Submitted communication, we have 1,050. Rejected communication, we have 290. Thank you for your attention. Now, I would like to invite the Dean of Faculty of Mathematics and Matter Science to give his speech.
بسم الله والصلاة والسلام على أشرف المرسلين. سيدي مدير جامعة أورجل المحترم، السيدة والسادة عمداء الكليات ومدراء المعاهد المحترمين، السادة الباحثين والمشاركين الأفاضل، حضرات الضيوف والزملاء الكرام، أهلا وسهلا بكم في انطلاق الملتقى الدولي الافتراضي للطاقة المستدامة والمواد المتقدمة الذي تنظمه كلية الرياضيات وعلوم المادة بجامعة قاسم مرباح أورجل. إنه لمن دواعي سرور انعقاد فعاليات هذا الملتقى العلمي الواعد الذي يضم نخبة عظيمة من الأساتذة والباحثين. يسعدني أن أستهل حديثي بالشكر الجزيل لكل من أسهم في فكرة انعقاد هذا الملتقى، وأخص بالذكر أساتذة قسم الفيزياء. كما يسعدني ويشرفني حضوركم الكريم افتراضيا، وأشكركم على ما بذلتموه من جهد في سبيل إعدادكم لأوراق هذا الملتقى الذي سوف يؤتي أكله ويحقق الأهداف المرجوة منه بإذن الله بفضل عملكم الغزير وإسهاماتكم الفعالة ونواياكم الصادقة. إن فكرة عقد ملتقى شامل أو يقترب من ذلك من أجل تعزيز أواصر التعاون والتعارف العلمي وخلق راهنية معرفية حوارية راقية. وقد اخترنا موضوع الطاقة المستدامة والمواد المتقدمة نظرا لأهمية الموضوع والإشكال، وإننا من خلال هذا الملتقى نحاول تأسيس وعي موضوعي يرتكز على سمة التبادل المعرفي يتجاوز سلبيات العولمة وما تدعو إليه من انفلات معياري وقيمي وتذويب للحدود وقتل الهويات والمرجعيات، وذلك بالاستفادة من إيجابياتها وتقنياتها الحداثية من أجل بناء جيل مجتمع يعي حدود رسالته ويرتكز على وعي معرفي أصيل يقدر قيمة العلم ويؤطرها من أجل تحقيق قيمة الإنسان في حد ذاته. وفي الأخير أجدد ترحيبي وشكري للحضور الكريم على تلبية الدعوة والإسهام في إنجاح فعالية هذا الملتقى. وأتقدم بجزيل الشكر والعرفان إلى السيد مدير جامعة ورقلة البروفيسور طاهر حليلات على ما يقدمه من أجل إنجاح فعالية هذا الملتقى وللجامعة ككل. والشكر موصول للكادر الإداري والبيداغوجي لكلية الرياضيات وعلوم المادة والذي يعمل بروح الفريق الواحد كلا حسب اختصاصه للوصول إلى الهدف المنشود، مؤمنين بالرؤية الشاملة والمتمثلة في بناء مجتمع المعرفة والوصول إلى الريادة العلمية وتحسين جودة البحث العلمي. وبدون إطالة أحيل الكلمة للبروفيسور طاهر حليلات مدير جامعة ورقلة من أجل إعطاء إشارة انطلاق هذا الملتقى، وشكرا.
بعد بسم الله الرحمن الرحيم والصلاة والسلام على المرسلين. أولا أشكر الحضور وأشكر عميد كلية الرياضيات وعلوم المادة وكل الفريق التابع لهذه الكلية من بيداغوجيين وإداريين على الدعوة الكريمة أولا، وعلى تنظيم هذا الملتقى الافتراضي الأول، والذي يعتبر يعني موضوع هام وهام جدا، وهو يتكفل بالطاقة المستدامة والمواد المتقدمة. ونحن في منطقة تحتاج إلى هذا النوع من الدراسات حتى نخرج أو نحل بعض المشاكل الموجودة في هذه المنطقة الصحراوية الجنوبية من الجزائر. كما أشكر كل المحاضرين والذين بعثوا بأوراقهم للمشاركة في هذا الملتقى الدولي من خارج الوطن ومن داخله، ودون أن أنسى كذلك الفريق الذي قام بإعداد والتحضير لهذا الملتقى من أساتذة الكلية، وكذلك الفريق التقني التابع لمدير الشبكات وهو الأستاذ كافي، مشكورا يعني على هذه المجهودات التي يقدمها في هذا النوع من الملتقيات الافتراضية. وجامعة ورقلة أصبح لديها يعني تجربة في هذا النوع من الملتقيات، ونتمنى أن ينجح هذا الملتقى يعني يخرج بتوصيات جيدة وتوصيات تخدم الجامعة وتخدم الطلبة وتخدم المجتمع بصفة عامة. إذن دون إطالة أعلن رسميا عن انطلاق هذا الملتقى. وفقكم الله والسلام عليكم.
سلام سيد كوزو. سلام.
السلام عليكم. نقدر نبدا؟
سلام سيد كوزو.
معك
أستاذ معك الأستاذ محمدي.
تفضل. أهلا وسهلا.
الآن يمكنك استقبال محاضرة البروفيسور ناصر.
أوكي. بسم الله الرحمن الرحيم والصلاة والسلام على سيدنا المرسلين. Ladies and gentlemen, firstly, I would like to thank the chair of the conference. I would like to thank also the rector of the conference. I would like also to thank the dean of the faculty. And I'm welcoming now for this great moment our professor from Switzerland, Naziruddin Mohammed Khaja, our great friend. So we would like to thank him for accepting to be among us today, and just to inform you that this conference is transferred to YouTube channel. So we will not see a lot of participants here in this speech, but the conference is transferred to the YouTube channel. So I will now try to introduce Professor Naziruddin Mohammed Khaja from PFL, what we call in French, Corps Polytechnique Fédérale de Lausanne. Donc, I will present him a short presentation, of course, of his biography. It's a rich biography that I will try to explain some of his research. So Professor Naziruddin is a professor of chemistry at the EPFL Science Campus, and his current research at EPFL focuses on perovskite solar cells and light-emitting diodes. He has published more than 25 peer-reviewed papers, 10 book chapters, and he is the inventor and co-inventor of over 93 patents. His work is high impact, has been recognized by invitation to speak at over 300 international conferences. He appeared in the ISI listing of most cited chemists and has more than 110,000 citations with an H index of 147. He teaches the functional materials courses at EPFL and Korea University, according to the Web of Science. In 2016, he is the 5th most cited chemist in the world, and he is one of the 19 scientists identified by Thomson Reuters as the world's most influential scientific minds in 2015. He has been named Thomson Reuters highly cited research from 2014 to 2020 and listed among the top 10 researchers in the perovskite solar cell research field by the Times Higher Education. I have to say that he's one of the leaders in the world about the perovskite solar cells. He is directing and managing several industrial, national and European Union projects. He has been appointed as world-class university professor by the Korea University and adjunct professor by the King Abdulaziz University in Jeddah. He has been elected to the European Academy of Sciences, fellow of the Royal Society of Chemistry, and fellow of Telangana Academy of Sciences. And he has won the 34th Khwarizmi International Award laureate in fundamental science. So welcome, Professor Naziruddin Mohammed Khazer, between us, and the floor is for you, or the screen is for you.
Thank you. Good morning, ladies and gentlemen. First of all, I would like to thank organizers for organizing this first international conference on energy materials, and in particular, Abdullah Kuju for inviting me to share some of our recent results. So I would like to share my screen. So the host has to allow me to share my screen. Can you allow me to share my screen?
Yes.
Okay. Wait a minute. The screen. Please, Mr. Kamal.
Yes.
Please share your presentation.
You can share your presentation.
I cannot share my presentation.
The green écran partagé. I think you have, Dr. Naziruddin, you have a menu on the bottom with the green, green
Yes,
button.
yes. And then it takes me to different folders. Let me just quit and then come back again. Maybe this may help.
Yeah.
Mr. Nasruddin,
Yes.
you can your screen, share your screen.
I'm trying to do that one, and it takes me to the Microsoft Drive, and so it's
So if it is problem, you can send me right now. You can send us right now the presentation, and we will.
yeah. That's what I'm doing.
Yes, send to me.
Yes.
Mohammed, I will send you right now the slides so you can present the slide. Okay.
Yeah.
I'm waiting. Okay, I'm waiting.
Monsieur Kuzu.
Yeah. أنا أسمع فيك. ابعث لي.
السلام عليكم.
السلام عليكم.
سي كوزو قول له البارتاجي عنده هو باش يخرج لا بريزونطاسيون تاع الشاشه الاكرون تاعو.
لا هو راه قال لك عندي مشكل في الميكروسوفت. كان بروفيسور نازر الدين.
Yes.
They give you the permission to have to share your presentation, I think.
Yes, but the computer somehow the presentation is not showing on the desktop.
Yeah, because you have to choose the right screen. You have to choose the right screen.
Yes.
Desktop. Yeah. So if it is possible, you can send us the slides. I will forward the slides to them so they can share with us all the slides, and you will make their presentation. Okay.
That's what I'm doing. I'm just sending the file.
Okay. I'm waiting for them.
Yeah. It says.
محمد راه يبعث لي يبعث لي السلايد وتديرهم عندك.
وي.
يبعث لنا البريزونطاسيون وانت مشيها وهو يهضر.
خلاص معليش.
ايه والله اعطيني انا تشير انا نشريها بنتحكم فيها. اعطيني البيرميسيون.
هاني معليش هاني نمشيها انا شوف معليش.
لا كيقول لي يهضر كيقول لك نيكست سلايد عقب وخلاص. ايه صح.
ايه معليش.
نستنى فيها تجيني الايميل هو عنده مشكل في الكمبيوتر تاعو عنده مشكل.
Sorry, so I have sent the file. Just wait. In 1 minute, you will receive it because the size is 300 gigabytes.
No, also the distance between Switzerland and Algeria is very far.
Yeah.
Yeah, I'm waiting. How is the situation in Switzerland? The health situation in Switzerland, is it good with COVID?
No, it's not good.
Ah,
It's not good.
not good. So you have to take care. You have to keep
Yeah.
all the time.
Yeah. The file has been sent. Can you just check with your email?
I'm checking. Not yet, but I'm checking. I'm checking that. Not yet. I'm checking. I don't know what happened, but not yet. Not yet. Not yet. I don't know what happened. I haven't received the. I'm waiting for the file, for the email, but
That's a notification. No, so the notifications adobe.com, isn't it? That's your email address?
yes.
Address.
Your email address.
Yeah, the email address, Kuzu, yes. I will send you an email now.
Yes.
Yes. I have sent you an email now.
Just wait. I'm sending again. Yes.
Yes. You have received my email?
Yes, I have received your email. I'm just sending it back.
That's good. That's good.
It's a sent again. Can you just please check?
But yes, I'm checking now. A few minutes. Okay. Okay. It's from switch. Okay.
Switch file. Yes.
Okay. It's okay. سي الازهر
وي
انا بعثت الازهر مبروك بالمبروك الايميل تاع الازهر بالمبروك
ايه ماشي
راه عندك ذاك
عندك الايميل
المهم راه عندك لحقك سي محمديه لحقك كبيره شويه
Were you able to download? Can you download?
We are going to download.
We are doing no problem, Professor. It's okay. It's going to download in the. We will finish in 1 minute.
Yes.
هبط الفيشيه.
Yes.
Wait a minute to complete downloading.
Yeah, okay, no problem. The size is big. It's about 300.
Yeah, 300 megabytes.
Megabytes. Yeah, that's why. Hope that we will not face any other interruption when you are present on your talk.
Yeah.
We hope so. Yeah.
مش عبد الله
نعم.
بالك نفوتوا الاخر يسموه بروفيسور كمال محمدي.
ايه.
ونطلبوا التيليشارجمون تاع لو فيشي هذا.
لا عندي راه عندي انا تيليشارجي راه تيليشارج تما. تحب تعطي لي سكرين انا نديرو معليش. انا خاص تقريبا راح بقى له شويه هكا.
يقدر هو يديرو. لا الاخر كوز يقدر يديرو. ماشي كوزو تقدر.
استنى ذاك ننزل راه ينزل ذاك حبس مش عارف بقاتو تقريبا كمل عندي انا بقاتو اقل من دقيقه.
راك تيليشارجي.
التيليشارج انا تقريبا كملته.
كملت.
لا تقريبا بقات لي 40 سكوند. ذاك يكمل ذاك يهبط ذاك ينزل.
يقدر il peut faire la commencer à introduire le sujet pour éviter le.
Yes, Professor Naziruddin, can you start talking about talk about the main subject of your presentation so that we can share the slide for everyone. You can start talking.
Yes, I have to see on the screen the slides. Is it possible?
Yeah. I will share now. I will share now with you with all. سي اعطوا لي لما باش نشير الفيشي معاكم قاعدين.
وعندك لما
اعطوا لي لما هذاك دقيقه خلاص عندي انا يمشي عندي انا. اعطي لي لما بركنا لك نشيريه. بكبير ثقيل شويه بكبير. تفتح على الحال. ايوه تفتح بارطاجي ليكرون. ايوه مشات عندكم شوفوا عندكم مشات.
Ça commence à voilà, c'est bon.
وي كاين.
ذاك تمشي خلاص. هاي تمشي عندكم.
نعم
تمشي الشيخ. نعم.
Professor Naziruddin, you can see the slides?
I can see the slides. That's fine.
Okay, just okay. Each time ask me next slide. Okay.
Or yes, so I have to do this one. Okay, fine. We can do like this.
Okay, each time ask me next slide. I will change the slide. Okay.
Okay, fine. First of all, I'm extremely sorry for this inconvenience caused by the miscommunication between my screen and your screen sharing application. Usually Zoom, we don't have any issues, but today, unfortunately, it happened. Without any further delay, I would like to present my talk on perovskite solar cells, a new paradigm in the energy sector. As Professor Kuju has introduced me, I'm working at EPFL, and I'm also having a position at WCU and King Abdulaziz University. Here in the bottom, you can see my email address. If you have any questions regarding my presentation, please feel free to send me queries. The next slide, please. Yeah, this is our campus. So here I will not spend too much time. So it's just only to show you this is our library, and we have this and Congress Center. So these are the new buildings which is having a ultra modern facilities. This is lake where we are located in a nice place. So you are all welcome to visit our campus. The next slide, please. So now what I'm going to show you is the comparison between the perovskite solar cells and silicon solar cells. You might be knowing all silicon solar cells, they have a power conversion efficiency of 26% as shown here. And the perovskite solar cells, the efficiencies are rising, and the highest efficiency today certified is 25.5. However, and if you look at the processing conditions of the silicon solar cells versus perovskite solar cells is compared here. On the left side, what you are seeing is you're getting the quartz from the mines, that's a silicon dioxide. Silicon dioxide is being converted into metallic silica, and the metallic silica is melted at very high temperature, 1,400 degrees temperature, and then followed by the crystal growth of this crystalline silicon material, and the wafering, and followed by we have a solar cells. All these processes are technologically very intensive, and the energy point of view, enormous energy intensive processes. On the contrary, look at on the right side, we are comparing the perovskite solar cells. So these are the cells which you can fabricate by solution processing. So what do you need here? So you need only 3 main layers. One is an electron transport layer. That's a typically titanium dioxide shown here on top of conducting glass, or it can be a tin oxide. So now we deposit perovskite material on top of it, and then I have a small, very thin layer of 2-dimensional perovskite. The students who wants to know more about this, you will see after 15 slides later, what is 2-dimensional perovskite. This is quite interesting material. You will see, you will learn a lot on these 2-dimensional perovskites. Then followed by, we have a whole transporting material. Basically, the perovskite solar cell has 3 main layers. One, electron transport layer, perovskite as absorber layer, and whole transporting material, spirometad. On the top, we have a contact. Now, by shining the light, we get the charges out and we collect electricity. At the same time, if we inject the carriers into the perovskite material, we can get the emission coming from this material, band gap emission. You can tune these emission properties by changing different cations or anions you will see in the next slide. So all this is happening by solution processing. But at the end of the day, you want to know what is perovskite actually. The perovskite is a very big family of materials having the oxide perovskites and then the absorbing perovskites. The one category which we will be discussing today is ABX3. A is a monocation, which can be inorganic cesium or methylammonium or formidinium as shown here. And we have a B cation, that's a lead, a tin, and halides are bromide, chloride, or iodide. So this is the ABX3 type of the perovskite. What happens is you take your lead iodide, mix with organic cation, and then they form a spontaneously 3-dimensional formation of perovskite layer shown on the left side. This materials has a very interesting properties are highlighted. Sorry, can you go back, please? One slide. Can you go back? One slide back. Yes, this materials has a very interesting properties as no, one forward. Yes, here. Yes, highlighted here. So I highlighted 3 important properties of these materials. The perovskite materials absorbs all the visible absorption spectrum from 400 to 800 nanometers, and you can tune the band gap of these materials by changing the cations or halides, and they have a remarkably defect tolerance property. And also very important property is a small excitation binding dissociation energy, which is less than 30 milli-electron volts. What happens is when you shine the light, we create carriers, and these carriers are collected at the interfaces. So initially, whatever we are doing by shining the light, we are creating the carriers, free carriers, rather than excitons. So the next slide shows you the spectral properties of this material. As we discussed in the previous slide, it absorbs all the visible absorption spectra starting from 400 nanometers to reaching up to 800 nanometers as described in this red curve. And wherever you excite this material, you have a very strong emission. Another interesting property is shown on the right side. You have a very sharp onset, and this sharp onset gives you the very important information that suggests that Arbach energy is very small, 50 milli-electron volts, and well-ordered microstructure. And this particular property is being used for the tandem solar cells. You will see in a couple of slides later what are the tandem solar cells. So with this one, I would like to go to the next slide to show the perovskite solar cells design configuration. So in perovskite solar cell community, there are two types of perovskite solar cells. One is called NIP, another is called PIN. So here we are describing the NIP structure. NIP structure typically has a conducting glass, and we deposit compact layer of TiO2, very small layer of TiO2. Then we have a mixed tin oxide and mesoporous TiO2 mixed oxide layers on top of FTO glass, followed by the perovskite deposition, a very thin layer of two-dimensional perovskite shown here, phenyl ethyl ammonium iodide as a two-dimensional perovskite cation and whole transporting material. So this is our typical configuration of perovskite solar cell in a NIP type. And if you look at the thickness of the perovskite solar absorber material, which is close to 600 nanometers. Now, using this configuration, on the left side is a cartoon just to give you the clear picture of our NIP configuration. Using this type of NIP configuration, we reach, in the next slide shows you the power conversion efficiency reached in our lab, which is 24.3%. Can you go to the next slide, please? Next slide gives you the power conversion efficiency is shown here. The short circuit current is very high, and the VOC is particularly quite significant, 1.15. And this type of data provides you 24.3% power conversion efficiency. So this is measured in the lab. So once we measure in the lab, so we have to certify to make sure that the data is certified in outside labs. So we have sent to Newport States, and there they have measured our solar cells on 27th of January. And then, yes, that's fine. Go ahead, please. One slide, next slide. The next slide. Next slide. Yes, here you can see the solar cells measured at Newport. The short circuit current measured in our lab is very much consistent with the measured at Newport lab, and the power conversion efficiency is comparable to the solar cell measured in our lab. So finally, we do have a 24 plus or minus 0.7% certified power conversion efficiency. And now using this type of technology, we started increasing the size. This size is very small, 0.05 square centimeters. Now we went to a larger scale as a scaling factor. Can you just go to the next slide, please? So shows you the scaling factor. Here we have a 6.5 by 7 centimeters mini module, and this mini module gives the power conversion efficiency of 21.7. So the scaling factor has a small difference in the power conversion efficiency, which is negligible compared to silicon solar cells. So in any case, so we have the mini modules, and these mini modules you can assemble into a 3x3 or 4x4, depending on our requirements. The next slide shows you this particular configuration. So here I just gave you a configuration, particularly on the right side. This type of small mini module can be useful for charging your iPhones. This is not the only one configuration. You can, depending on our requirements, voltage output and current output, you can assemble them into different fashion, either serially connected or parallelly connected. So the technology is maturing. The next slide shows you the importance of the tuning properties. Tomorrow, if we want to have a different colored panels, it's possible to with the perovskite solar cells. That's not the case with the silicon solar cells. Not only tuning the color of these materials, you can also deposit these perovskite materials on a plastic substrates as shown on the next slide, so that the weight of these perovskite solar cells using plastic as a substrate is extremely low. In other words, power output versus the weight of the perovskite solar cells is very high. And this is the highest power output with respect to the weight of the perovskite solar cells available today on the Earth. So using this type of plastic substrates, all the applications using UAV, that's a autonomous aerial vehicles can be used this type of plastic solar cells. Not only for this type of applications. And the next slide shows, because I have given last week presentation in DIVA. So since I have given presentation in DIVA, I have taken Dubai as an example. So imagine covering all these buildings or clothing these buildings with our perovskite solar cells will become the power generating houses. So all these buildings one day will become independent. So these are the important aspects of this perovskite solar cells. So now there are several companies working in silicon solar cells. They want to adapt these perovskite materials on top of silicon solar cells for a tandem configuration applications, because the silicon solar cell efficiency, we have reached its limits, thermodynamic limits. So we cannot increase the silicon solar cell efficiency beyond what we are having today. So the one approach is, the next slide shows you the possible approach to increasing the power conversion efficiency of silicon solar cells by combining perovskites on top of silicon solar cells. So this is publication came very recently. Al-Ashuri, this is a student who worked in Berlin group, and they published this work. So if you look at the A panel, which shows a silicon solar cell terminating with the end, and now we have a recombination zone, that's a ITO. So where the electrons are coming from the silicon solar cell, recombines the positive charges coming from the perovskite solar cells. And now in between we have a whole transporting material, which you will see clearly. It's called SAM. That's a self-assembled monolayer, or PTA. This is a polymer. This is a very thin layer of whole transporting material deposited on top of ITO, followed by the perovskite. And now we have an electron transport layer on top of a perovskite. That's a tin oxide, and followed by this anti-reflecting coatings. So this is the cell configuration. So this is typically what we call PIN configuration. And this is the cross-sectional image, and the power conversion efficiencies using various whole transporting materials are shown here. But if you need more details, please refer to this publication, science publication coming from Al-Ashuri. Now, the next slide shows you the power conversion, certified power conversion efficiency of this tandem configuration, which is 29.15% certified power conversion efficiency, certified at Fraunhofer Institute. And if you look at the E panel, that shows the EQU data of the perovskite solar cells, and at the same time, silicon solar cells. And if you look at compare the short circuit current, which is a 19.4 coming from the perovskite solar cell, and the silicon solar cell giving 20 milliamp short circuit current. So because the currents are matching, so it's a current matching a tandem configuration. And now if you look at the F panel, so that shows the newly developed whole transporting material. That's a self-assembled monolayer whole transporting material, which has a 95% of its initial efficiency, compared to the very popular whole transporting material, that's a PTA, that leaves only up to 150 hours, and then the stability decreases significantly. So this shows the new whole transporting material has a huge prospects for stable tandem configurations. Now I take to the next slide. The future is even brighter if we start using bifacial devices, silicon solar cell devices. Within the bifacial devices or in the silicon solar cells also, you have two types of configurations. One, a 4-terminal. The previous configuration which I have shown you is a 2-terminal, where you have to match the current so that the output will be the product of 2 cells current and the 1 cell's current, and then the voltage of the 2 cells. And this can be independently improved if we have a 4-terminal configuration. So in other words, take home message is the future for the perovskite silicon solar cells using bifacial silicon solar cells is very bright, and the power conversion efficiencies can reach over 30%. But recently there is another publication coming from KAUST. Can you just go to the next slide, please? Next slide. Yes, this is the publication coming from KAUST. Stefan Dolf, he's the senior author. He has built the he has taken the bifacial silicon solar cell, again deposited nickel oxide. In the previous case, it was a self-assembled monolayer, and now here it's a inorganic cold transporting material deposited on top of bifacial silicon solar cell, followed by perovskite material, electron transport material, and the cross-sectional image is shown here. On the left panel, A panel, you can see the possible the light absorption phenomena. From the top, you have a direct, and from the bottom, you have an albedo effect, and the reflected light can be absorbed using this material. So that's the importance of this bifacial configuration. So this is just a proof of concept. The efficiencies are in the range of 25%. They obtained. Now we go back to the next slide, please, to show the importance. No, next slide, please. Sorry, one more, one forward. Yes, one more. Yes, here. Now, if you look at the importance of the perovskite solar cell versus silicon solar cells. So here I have given the primary energy demand. That's a energy required to manufacture these solar cells. And now, if you look at the second, that's the energy payback time. We are comparing here the silicon solar cells perovskite tandem configuration, CIGS perovskite tandem configuration, followed by the thin layer and perovskite tandem configuration, perovskite tandem configuration. The primary energy consumed, and this energy to be generated by the solar cells requires only 1 month for the perovskite solar cells. For comparison, silicon solar cells, they may require over 1 year time. So that shows the primary energy consumption of these solar cells. Fine, everything is going very well, but what's the problem? Why these cells are not in the market? The next slide shows you the issue. What is the issue? We have a perovskite solar cells, 25.5% efficiency, extremely good, comparable to silicon solar cells, which is 26%. Even the tandem solar cells has a 29% efficiency. But what is missing in perovskite solar cells is highlighted here, stability. But now my topic starts here. How do we increase the stability of these materials? So this topic I targeted for the students because it generates a lot of new ideas, and the students can come up with their own thinkings and to develop new materials. So now to increase the stability, I have highlighted in the next slide 3 aspects. So interface engineering, compositional engineering of perovskite layers, the development of charge transport materials. So in these 3 layers, one can be sure that to get the enhanced stability. So what you will see in my presentation is what is actually interface engineering and what is it is doing to the perovskite materials. How can we improve the perovskite stability by changing the composition of the perovskite absorber layer? And you have seen the inorganic cold transporting material and the newly developed self-assembled monolayer cold transporting materials. Can we further develop new cold transporting materials to increase the stability of these materials? That's what you will see in my presentation. So stop me whenever my time is over. So I will continue describing the research which we have done to address these 3 issues. The next slide shows you the difference between the 3-dimensional perovskite and 2-dimensional perovskite. On the top left side, what you are seeing is a 3-dimensional perovskite. When you mix this lead iodide, it's a corresponding organic cation. It self-assembles into 3-dimensional framework, and it's called 3-dimensional perovskite. And here we have a cation that goes into this cavity. If the cation size is bigger than this cavity, what it is called Goldsmith tolerance factor. And then we don't have this 3-dimensional perovskite. We slice this 3-dimensional perovskite into low-dimensional perovskite. Now in the low-dimensional perovskite, you have a different configurations. One possible configuration is only 1 layer of 3-dimensional perovskite, that's a low-dimensional perovskite, 2 layers joined together, or 3 layers joined together. So this gives you, the students, the beautiful opportunity to combine the bigger cations and the smaller cations to get their required number of perovskite layers so that they can be extremely stable. Now, just to focus on the extreme right side of the panel, we are comparing the absorption spectral properties of these two materials. Three-dimensional perovskite, which absorbs the whole visible spectrum, but we have issues, that's the stability. On the contrary, the two-dimensional perovskites are extremely stable, but has a problem of absorbing very small portion of the visible light. So can we combine these two properties into one and then develop a perovskite solar cells? That's what you will see in the next slide. I'm showing you the characterization techniques of these materials, putting two-dimensional perovskite on the top of three-dimensional perovskites. So before I go, let me just give you the composition. So here we are showing C is a cesium, F is a formidinium, M is a methylammonium, P is a lead, iodide, and bromide. This is the composition of our perovskite, and the constituent amounts are given on this here. Now we put the layered perovskite.
Should they have
Hello?
Yes, you can continue. Yes, yes.
Yes, we deposited a layered perovskite on the top of three-dimensional perovskite. Now you can see the characterization techniques. One, we are using XRD. Now on the right side, B panel shows the absorption spectral properties of the two-dimensional perovskite. That's a phenylethylamine lead I4. So this is the composition, and this is the absorption spectral properties. As we discussed, the two-dimensional perovskite absorbs only a small portion of the visible light. And the black line is our reference sample, three-dimensional perovskite. And now if we deposit this two-dimensional perovskite on the top of three-dimensional perovskite, the red line is shown here. Now, how do we know that this is happening? Now, if you look at the pure two-dimensional perovskite, which is shown here on the green, the top line, this is a characteristic fingerprint line of the two-dimensional perovskite in the XRD data. That's a phi 2 theta. And now if you look at the bottom, that's a black line. We have this around 14.9. This is a characteristic peak for the three-dimensional perovskite. On the middle, you do have a two-dimensional perovskite peak, at the same time, three-dimensional perovskite peak. Now, this is just XRD data. Now, if we go to the luminescence properties, can you just go to the next slide, please? So since we are depositing the two-dimensional perovskite on the top, you should be able to see whether this perovskite layer is there or not. So by exciting at 450 nanometers from the top side and corresponding emission spectra, you can see this is the red line. Now, if you look at the reference sample, that's a black line. Excite at the same wavelength, you see the black emission, the emission black line emission coming around 780 nanometers. That's due to a pure three-dimensional perovskite. So this is another evidence to demonstrate that the layered perovskite is deposited on top of three-dimensional perovskite. Now, another question is it only on the top, or does it penetrate through the bulk to the bottom? Now, if you look at the two samples again, that's a reference, that's a black line, and then the two-dimensional perovskite deposited sample, that's a red line. If we excite from the bottom side, so the two emission spectra are overlapping. So this demonstrates that the two-dimensional perovskite is only on the top of three-dimensional perovskite. So it's well, what is this two-dimensional perovskite is doing to our perovskite solar cells is shown on the next slide. So here, by using the UPS data, we constructed the energy level scheme, and based on this energy level scheme, you can see when by shining the light, we create charges in the perovskite, that's a positive charges and negative charges. But if you look at the HOMO level of this two-dimensional perovskite, which is well aligned with the three-dimensional perovskite, so the positive charges which are generated in the perovskite, they will tunnel to the whole transporting material. At the same time, the electrons which are generated within the perovskite layer, they will be blocked here and driven towards the ETL layer. So what is happening is here, we are reducing the recombination because of the presence of this two-dimensional perovskite. And how do we know that this is happening? Can we just go back to the one slide back, please? Back one slide. Yes, here. Look at the VOC, that's open voltage. The blank has a 1.08 volts, and then the two-dimensional perovskite has a 1.14. The small increase in the VOC is a manifestation of reduced recombination at this interface. Now, using this type of configurations, the optimized efficiency, you can reach 21% at that time. Now, you have seen this, the beauty of depositing the two-dimensional perovskite on top of three-dimensional perovskite. Now, what it is doing actually to your perovskite solar cells is shown on the next slide. Yeah, so this slide shows the stability data of the reference sample. That's a pure perovskite solar cell without any two-dimensional perovskite. The red line shows the stability data over 800 hours of the perovskite solar cells deposited with the two-dimensional perovskites. There are two types of curves. One is a blank, another is a filled one. The blank one is the stability data measured under argon atmosphere, and then the filled ones are under normal conditions, ambient conditions, with encapsulated with the glass. Now both are overlapping. However, compared to the reference sample, the two-dimensional perovskite deposited perovskite solar cell shows extremely stable performance. So this is the beauty of demonstrating a stable perovskite solar cells by interface engineering. Now, so here these comes. This is the only cation, phenylethylamine, that is working? No, the next slide shows there are two. Though we have worked hundreds of cations, but I have highlighted only two cations, which is a fluorophenylethylamine, and the second one is pentafluorobenzylamine. So these are the two cations. We can make these perovskite solar cells. The absorption spectra properties are shown here. Again, the two-dimensional perovskite deposited on the three-dimensional perovskite are shown on this in this curve. So the next slide shows the power conversion efficiency of these materials. So if you look at the A curve, that's our blank, the power conversion efficiency is 20% with 1.09 volts. When we deposited the two-dimensional perovskite involving fluorophenylethylamine, the power conversion efficiency increased from 20 to 21%, and the VOC went from 1.09 to 1.13. Changing the cation from fluorophenylethylamine to pentafluorobenzylamine, that's on the red line, you can see the VOC further increased from 1.13 to 1.15. The power conversion efficiency increased further to 21.65. It's a small increase in the power conversion efficiency, but the stability is remarkably high compared to our reference sample. So the reference sample is a pure three-dimensional perovskite, and now we have a red line, which is a pentafluorobenzylamine involving the two-dimensional perovskite cation, shows extremely stable performance. So this is, we classify this as an interface engineering to enhance the power conversion stability of the perovskite solar cells. The next few minutes, we will discuss the compositional engineering of perovskite layer. So let's say, next slide, please. So here, what we are doing is, so on the top, I'm showing you the three cations: methylamine, formidinium cation, then we have a guanidinium cation. So methylammonium and formidinium, they form three-dimensional perovskites, and the cations, when we have these cations, the tolerance factor, they come within the 0.8 to 1. So within this tolerance factor, the perovskite layers, they usually form cubic, this is a cubic zone. And if the cation is too large, they don't form the perovskite. And if it's too small, they don't form the perovskite. Guanidinium comes under this category. But next slide shows us, shows that we have combined this, the smaller cation, 75%, and the bigger cation, that's a guanidinium, which has a 3 NH2 groups, around 25%. by combining this smaller cation and the bigger cation, we can stabilize the perovskite because of the enhanced hydrogen bonding shown in this cubic unit. The cell configuration is, as we discussed previously, that's the NIP configuration. The power conversion efficiency in the range of 20%. But if you look at the stability data, that's a red line, with 25% of guanidinium, and compared with the black line, which is our reference sample, over 1,000 hours, the stability is remarkably stable, having guanidinium as an additive. So why this is happening? It's because of enhanced hydrogen bonding coming from the guanidinium. So this shows the stable performance having the compositional engineering. So I take two more examples. In the next slide, one example is on the ionic liquid. So here, so there is one ionic liquid we have selected. This is called functionalized ionic liquid. What we are having here is fluorinated chain, the ionic liquid. People who are working in perovskite solar cells, they understand there are issues with the perovskite materials. That's called hysteresis. So this hysteresis is due to three reasons. One is imbalanced charge extraction. Second is ion migration. So this ion migration is because these perovskite materials are ionic compounds. So can we increase the ionic composition by doping the perovskite with ionic liquid? So instead of doping pure ionic liquid, can we functionalize so that this material can act as a functionalized ionic liquid? So the cell configuration is shown on the B panel. This is similar to our previous configuration, NIP, followed by the spectral properties are shown here. There is not big difference when we are using 1%, 2%, or 4% ionic liquid. The spectral properties remain the same. But however, if you look at the focus on the panel E, the XRD data, this peak corresponds to the perovskite peak, particularly 12.6 peak corresponds to the formation of lead iodide due to the decomposition. Now, if you look at the black line, that has a lead iodide, that's our reference sample. When we use 1% lead ionic liquid, you see the red line, it's decreasing the formation of lead iodide, followed by a 2%, that's a green line, followed by 4%, that's a blue line. So by adding this ionic liquid, we can suppress the formation of lead iodide. That's due to the decomposition of the perovskite layer. So the next slide shows the beauty of having 1% of this ionic liquid into the perovskite composition. So on the right panel, what we are seeing is the front side and then the back side with 1% ionic liquid doped perovskite solar cells. On the left side, as a reference sample, over 2 months period, when we expose to the ambient air with a 50% humidity, the perovskite, the color is disappearing. The presence of 1% ionic liquid clearly shows the enhanced stability of this material. Now, the question is for students, what is doing this ionic liquid? Next slide, I just put the information so that they understand what is happening here. So since we are using functionalized ionic liquid that has a fluorine as a functional group, we have a fluorine as a binding energy. The XPS data here is shown the fluorine binding energy, and in the perovskite solar cells, we have focused on only few grains. With our focused ion beam, we are etching from top to bottom up to 75 nanometers. Now the results are also here on the A panel. At the zero, at the beginning, we have a fluoride binding energy coming around 688, and up to 25 nanometers, you can see the blue line. The moment we reach up to 50 nanometers, there is no binding energy. So what this information, how do you interpret this information? What's happening here is the fluorinated compounds are insoluble in organic solvents where we are using the perovskite layers. So this organic compound is floating. When the perovskite is forming, so this fluorinated compound is forming a shell on top of the perovskite grains. And that's a completely unexpected data which we have obtained here. So using this type of configurations, we obtained close to 20% efficiency. Efficiency is not important. What is important is showing the stability of these perovskite materials. The next slide shows the stability. So here, just focus on the insert, the reference sample versus with 1% iodine, with 1% ionic liquid. So the XRD data clearly shows the formation of lead iodide at 60 degrees temperature. As the time goes on, this formation of lead iodide increasing. That's a manifestation of decomposition of the perovskite. And this is not happening when we have a 1% of ionic liquid in the perovskite composition. Okay, so the next slide shows I have taken another ionic liquid as an example, because this gives you the strength of the materials development. Here is the new ionic liquid with the double bond. So you can polymerize this double bond group. So when at 80 degrees temperature, these ionic liquids, they self-polymerize. So here is the perovskite solar cell configuration, similar as the before, but we have selected intentionally very unstable perovskite, that's a methyl ammonium lead iodide, and we use this ionic liquid 2%, and using this 2% ionic liquid, we obtained 17% efficiency. The reference sample is only 15% efficiency. But we changed the composition of the perovskite. The next slide shows the different composition. That's a formidinium, methyl ammonium. This is a black line is a reference sample, IV characteristics, which has a 17%, changing from methyl ammonium, that's a 15%, to formidinium and methyl ammonium mixed cation perovskite, that gives you 17% efficiency. With the 2% of ionic liquid, we get 20% power conversion efficiency. So, but however, as I mentioned, the purpose of using these ionic liquids are just to demonstrate the stability. So the next slide shows the stability of this ionic liquid. And the black line is a polymerizable ionic liquid. So if you look at the two ionic liquids, so we have mimic, this is a unpolymerizable ionic liquid on the right side. On the left side, we have a polymerizable ionic liquid. So in both cells, we use, in one cell, we use the polymerizable ionic liquid, and another cell, we have used unpolymerizable ionic liquid. The stability data shown are here. The polymerizable ionic liquid, after 2000 hours, the initial efficiency remained 90%. However, without any polymerizable groups, the ionic liquid, the power conversion efficiency decreased 40% of its initial efficiency. So the difference in the stability data is a manifestation of this double bond, which is forming a self-assembled polymer layer within the perovskite composition. So with this one, I completed my composition engineering of perovskite layer, and the remaining last 5 minutes, I will focus on the charge transport materials. Can we go to the next slide, please? Yes. So here we focus on the charge transport materials. So let's take the next slide. So particularly whole transporting material, let's focus on the whole transporting material. That's a spirometad. It's a very popular whole transporting material, which gives over 25% efficiency of the perovskite solar cells. On the left side, we are showing the cell configuration energy level scheme. This particular whole transporting material has a few challenges, and particularly the main challenge is the mobility of this material is very low. So how can we increase the mobility? So the next slide shows the many groups in the world, they are using this type of dopants to enhance the stability of this whole transporting material. Cobalt, this pyrazine pyridine type of ligands, tris complex, TFSI, tertiary pyridine. Next, click on next again. Click once again, please. Click, click, click. Yes. So using this type of dopants, what we do is we take the intrinsic material, we remove one electron from the whole transporting material, and then this becomes extremely mobile molecule, a conducting material. But as a result, because of these additives, now if you look at the contact angle measurements, without any dopants, the contact angle is 77. With dopants, the contact angle is decreasing. So that means it's becoming like hydrophobic. The second disadvantage is the tertiary butyl pyridine is being a nucleophilic. It attacks to the whole transporting material, making it unstable. So the purpose here is to develop new whole transporting materials, shown in the next slide. Here we have developed, next slide, please.
This okay?
Next slide.
Yes, I'm trying to do.
Okay.
I have problem, I think. Yes.
Yes. Okay. Thank you. So this is a new whole transporting material which we have developed and published in 2017. 2016. And here we have a thiophene. So the purpose of showing this molecule is, so can we enhance the interaction between the whole transporting material and the perovskite layer? And on the B panel, this is calculations done by Professor Filippo De Angelis, and he clearly shows, the calculations clearly shows that's an enhanced interaction between the perovskite and thiophene groups. So we using this type of whole transporting material, though, and we obtained over 20% efficiency. Next slide shows the power conversion efficiency. Yes. So here is the power conversion efficiency in the cross-sectional image of the perovskite solar cells, comparison with the spirometry. So the comparable results were obtained. So here the beauty is to have these thiophene groups to have a better interaction with the interface. So can we further modify these whole transporting materials so that we don't have to dope at all? The next slide shows the new design concept. Next slide, please. Yes, here we have a design where a disc type of triazotexurine as a core unit. Since we have identified the thiophenes as a possible arms, so we incorporated 3 arms onto this unit with monothiophene, dithiophene, and trithiophene. And now if you look at how these molecules are adsorbed on top of perovskite is shown on the next slide. So they go like a columnar attachment on the top of perovskite solar cells. So using this new approach, so we don't have to dope. So once you create positive charges, they tunnel through these columns. The next slide shows the efficiency of these whole transporting materials. Next slide, please. Yes, here, just focus on the KR321, which has a 19% efficiency. The KR321 has a 3 thiophene groups, triazotexurines, and similarly, the spirometry under same conditions gives the similar efficiency. But the difference between these 2 whole transporting materials, spirometry is doped and KR321 is undoped molecule. So this is the beauty of this undoped whole transporting materials to see the enhanced power conversion efficiency and stability. And we recently developed new whole transporting materials. Can you just take the next slide, please? Next slide. Yes. So here are now based on this, So based on these thiophene units and the donor groups, so we came up with this type of new molecules, which are in the small. But if you look at the stability data, the one of this molecule, this is BT4D. The data is shown here, BT4D. Over 1,200 hours, the initial efficiency remained 98% of the initial efficiency. Under similar conditions, the spirometry, the efficiency decreased to 0.79. So these are the types of whole transporting materials the students can think of for coming up with the new molecules. So the next slide shows the electron transport materials. So here is the data based on the 3 different types of electron transport materials. On the bottom, that's a black line. It shows the stability data of our perovskite solar cells when we use only TiO2 as electron transport materials. However, if we change the electron transport material to pure tin oxide, the data is shown it's buried under the blue lines. So it's extremely stable. And at the same time, we can also manipulate having TiO2 followed by tin oxide that's a blue line. So that's a mixed oxide layer. So this work you can see more details in applied energy materials. So this using this type of electron transport materials, we reach to over 21% power conversion efficiency. So I have demonstrated interface engineering and demonstrated. Can you just take to the next slide, please? Next slide. So in my presentation, what I tried to show you is how to increase the stability by combining the two-dimensional perovskite and three-dimensional perovskite. That's interface engineering that reduces the recombination and increases the stability. At the same time, I have shown you the composition engineering of bonadinium and the different organic cations that enhances stability, and the ionic liquids containing hydrophobic groups also enhances stability, and the new whole transport charge transport materials we showed enhanced power conversion efficiency. With this one, I would like to thank my students. The next slide shows my students. Next slide, please. Yes, here are my students and postdocs, collaborators. I would like to thank them for their contribution. Okay, the next slide shows the
السلام عليكم.
وعليكم السلام.
السلام عليكم. سكر المايك تاع الجماعه، كل واحد سكر المايك تاع الجماعه اخرى. كل واحد سكر له المايك تاعو، كل واحد سكر له المايك تاعو. اللي داير الفيديو نحى الفيديو، اللي داير الفيديو تراه نحى.
السلام عليكم. هو كاين مشكل الصوت، انا نسمع في الحس محل الصوت.
لا سكر لهم الصوت تاعهم، سكر جي معاه بالواحد خرج شوف لي بارتيسيبون، كليكي على لي بارتيسيبون وابدا سكرهم في اللغه تاعك. بس انا تشوفني اذا نقدر انا، اذا نقدر شوف اذا نقدر انا لكن نسكرهم. عيب عليه.
Nasruddin, thank you for your presentation.
Yes.
Okay, thank you.
Mr. Kuzu.
If we have questions, yes. Now let's read. We have a lot of, I think we have a lot of questions here. So we don't have enough time. So I will ask from my side one question or two questions only. So because we are late. So the first question, the first thing, thank you for your nice presentation, which is very rich. And with high quality. I think all the participants have benefited from this great presentation. So I have two questions. It's general questions. So the first one, in your slide, you have not presented some kind of what's the mechanical constraints of the perovskite solar cells. And the other thing, the chemical, I mean, we think that there is some problems compared to the conventional silicon solar cells. There are some problems of chemical problems that we need to use some green chemical, what we call the green chemistry, to use in the perovskite solar cells, and what are the disadvantage of the concept of the mechanical constraints of the perovskite solar cells?
Yeah, so the one main constraint we see is the mechanical strength of this thin layer. And if you look at the silicon solar cells, which has a typically 300 micrometers. So now they are even getting thinner, 250 micrometers to 300 micrometers thickness. But here what we are having is a perovskite absorber material less than 1 micrometer. So the mechanical strength is 1 Vernier. So this has to be improved by encapsulation techniques. I think once if we encapsulation technique, we should be able to make these materials stable and do the good job for the efficiency conversion.
Yeah. There is another question from Dr. Boubiev from Batna. So he asking, what about the temperature? If we can use our in desert, in Algeria, in the south of Algeria, the temperature is very high. So what are the impact of the temperature compared to the other solar cells, conventional solar cells?
Yes, this is very important question which your colleague has asked. The temperature is still an issue. Why temperature? Because when you take the perovskite material as at room temperature, it's a tetragonal phase. So if we increase the temperature to 60, the phase transition is happening and it's forming, going from tetragonal to a cubic phase. So there is a small change in the phase transition. But this is not happening in silicon solar cells. Silicon solar cells can tolerate very high temperatures. So that's the reason why we are subjecting these solar cells at 60 degrees temperature. But however, 80 degrees temperature stability is required. So we are trying to understand and then modify the composition to get the stable performance.
Okay. Thank you for this response. There is another question from Professor Kamal Mohamdi from Boumaddas University in Algeria. So what is the potential of perovskite mineral availability in which countries?
Yeah, so the mineral of, that's a lead mineral, isn't it?
Yeah.
Yes.
Mineral resources, yeah.
Yes, this is a byproduct of platinum group metals. And most African countries, they do have this material in a significant quantities. And also imagine we are using only less than 1 micrometer. So maybe 32 kilograms is sufficient to produce megawatts of power conversion efficiency, such a small quantity required. But however, the mineral is available.
Yeah. Okay. There are a lot of comments from participants thanking you for this nice presentation. And I have here maybe last question. It's a general question for everyone. Can simulation efforts give insight into electrical parameters prior to experimental efforts? This is a general question, of course.
Yes. There is one group at APFL, Professor Ursula. She is working on this understanding of how we get this type of perovskite materials and different phases. The simulations can greatly enhance our understanding of the mechanical properties, but not the electronic or how the electrons are moving. So not this one, but the materials property, we can get a lot of information by simulations, surely.
Okay, thank you very much. So now we have to finish our this session, and we ask all the participants if they have questions, they can address all the questions to Professor Naziruddin. So we can give you his email, of course, so you can ask him the questions via email. Thank you for all. Thank you for the organizer, and see you in the next session for Professor Mohamdi Kamal about the energy transition pathway simulation and energy realms. So we'll start the next, in a few minutes, we'll start the next presentation of Professor Mohamdi Kamal from University of Boumaddas. Thank you, Naziruddin, and see you, inshallah, next time at a conference.
Thank you for inviting. Thank you for organizing this conference. I appreciate it. All the best. Bye.
Bye. شيرمان راك هنا شيرمان
شرمانة.
راك نبداو اسمع قول للجماعه قول لهم من فضلهم الكاميرات تاعهم يسكروهم الكاميرات راهم ينقصوا الديبي تاع الانترنت ثانيا اننا احنا رانا نشوفوا في الكونفرنس ماناش نشوفوا في الكاميرا تاعنا اش راهم دايرين من فضلكم يا جماعه الكاميرا اللي دايرين الكاميرا يطفوا الكاميرا تاعهم من فضلكم يا جماعه s'il vous plaît éteindre vos caméras s'il vous plaît please switch off your camera please. This is a conference. We should not say, please stop your cameras, please. شيرمان تفضل. الناس راه داير واحد داير التليفون تاعو واحد والله انا ما فهمتش انا يا من فضلكم يا جماعه اللي عنده كاميرا يطفيها. عندك المايك والكاميرا طفوهم المايك والكاميرا تقدر تطفي لهم الكاميرا والمايك من عندك على بالك. استاذ محمد كمال موجوده. استاذ محمد you are here.
I can't share because you must.
Yes. I must leave because I have another conference, so I have to move to another conference. So I will leave this and thank you very much for this nice conference and hope the success for the next presentation. Thank you. Assalamu alaikum.
Thanks, Professor Kuzo.
Professor Kamal,
Yes.
could you start your presentation?
Yeah, so we try to share here. Yes, you tell me when you see the slides. Can you see the presentation? Est-ce que vous voyez la présentation?
Can you start?
Yes.
Could you start?
I'll just to go out of the. Okay.
Voilà, conférence.
Okay, I hope I have maybe 20 minutes or 30 minutes. Okay, Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, good morning and Holy Ramadan for all of you. So this presentation is about energy transition pathways, and we will use or we will talk about a decision-making tool, En-ROADS, which will take into account the energy resources and the policies about energy transition in order to make some provisions about 2050 or the mid-century development strategies with net zero or low carbon development. So I have some problems to move the slide. Yeah, it's okay.
Come on.
Yeah.
Your sound is low.
The sound is low. Oh. Can you hear me?
Could you augment your sound?
I will try to do that.
Increase your sound, please.
I think I don't know if you can hear me like this.
Yes, yes.
No?
Yes.
It's okay?
Yes, I can hear
Now
you.
I have a,
Yes, I can hear you.
I have to move this this window. I don't know what's happening with
فيريفيت لا بوست بدك تجبد دراهمك ما مش دايرين لك خلاص حبسوه
please can you
زيا
is it okay now?
Monsieur Kamal, activez le son, s'il vous plaît.
Si, j'ai activé le son. J'ai activé le son. Donc, j'ai activé le son. Est-ce que ça va mieux, donc non?
Oui, oui. Oui, oui.
Très bien. J'ai un problème de fenêtre qui ne veut pas partir. Voilà.
Bon.
Okay, we know that there are a lot of science and data that support that the next years we will experience some disasters due to climate change and climate crisis. So the IPCC, which is the United Nations scientific tool, has planified 4 or 5 pathways called representative concentration pathways, we will see later, to keep the concentration under 400 ppm of course, carbon dioxide emissions, and also to keep the final temperature of the ambient temperature in 2100 below 2 degrees. And we know that one of the most sectors which is responsible of most of the emissions is the energy sectors used for electricity or in industry, transport, buildings, etc. Even if when we see the energy demand in the beginning of the century to 2010, we see that in fact the demand is fluctuating due to the World War II, for example, the Spanish flu or financial crisis, and now we are experiencing this sanitation crisis with the COVID-19, and we see that the energy demand has dropped. And the energy transition now, we need, of course, every country needs to know what energy mix it has to use in order to get the net zero emissions in 2050. So the energy transition pathways are guided by 2 things: the 2030 Agenda Goals for Sustainable Development Goals and the Paris Agreement on Climate Change, which is articulated through nationally determined contributions and long-term low emissions development strategies. And since this COP21, most of the countries have committed to reduce their greenhouse gases emissions. For example, in case of Algeria, they committed to reduce by 7% by 2030 their emissions. Now, if there is, of course, some subsidies from international subsidies, then this 7% can go to 20%. And of course, Sustainable Development Goal 7 provides clear targets to be met on universal energy access, increasing renewable energy, and improving energy efficiency. These targets require radically transforming our model of consuming energy systems to a low carbon model if we are to limit global warming to a maximum of 2 degrees. So I will use this En-ROAD tool, which is in fact a big challenge because due to the complexity of interconnected sectors, social, economic, environmental, etc. So we need, in fact, a tool. This tool is, of course, designed for, authorities, for people, for students, for everyone that can give his advice on the next energy mix we could have in 2030 or in 2000. So this, in fact, this tool was founded by Elizabeth Sawin and Andrew Jones from the MIT. And the objective, in fact, is to get some climate workshops and climate action simulation or games in order to make people conscious of the disasters that climate change could cause to our planet. So I will talk about En-ROADS here. In fact, En-ROADS explores is a solution simulator that models policies for energy, transportation, land use, and new technologies to limit climate change. While you have C-ROADS here, which is another tool, which is similar to this one, but this one is focusing on countries, while the En-ROADS is focusing on solutions. And you have a third one, ALPS, which focuses on agriculture. Of course, all these tools, simulation models, are found here in the Climate Interactive website. And the En-ROADS tools achievements have briefed dozens of US senators in the United States, representatives, and their staffers from both sides of the aisle using En-ROADS simulation. Together with the partners in Atlanta, for example, they have created shifts in spending and policy that improve both racial equity and climate resilience. And the concept of multi-solving we talked about also, coined at Climate Interactive, is being put into practice in local communities, cities, states, and nations around the world. Because in fact, now the approach is to say that, of course, the solution must be local, while we have to think global. So to give a final word about En-ROADS. En-ROADS stands for Energy Rapid Overview and Decision Support. So it's a decision support system. En-ROADS is an open and freely available policy simulation model that offers decision makers, educators, businesses, media, and the public the opportunity to explore for themselves likely climate consequences of energy, economic growth, land use, and other policies and uncertainties with the aim of improving their understanding. So this is the flow sheet of the En-ROADS that you can see when you download, in fact, when you go to the En-ROADS Climate Interactive website. So I will make a demonstration just at the end. So here you have, in fact, the energy supply, so coal, oil, natural gas, bioenergy, renewables. And you have here some levers that you can just push in order to reduce or rise, depending on the resources you have in your country. For example, in China, we will use more coal than oil, while in Algeria, for example, we will use maybe more natural gas than coal or nuclear, for example. if you go to France, France has nearly nuclear resource as a source for electricity production. And you have also the sector, the transport sectors, the building and industry, and you have also the growth, the economic growth, the population that could affect this final temperature. So we must keep this temperature under 2 degrees. And we have to shift from the business as usual here in black to a more clean model using the current scenario that you have chosen yourself. So the anode core structures, so it's about reducing total greenhouse gases, because these greenhouse gases, particularly dioxide carbon, is has influence on temperature and has impacts, of course, on the environment and disasters, etc. So these greenhouse gases are coming from many sectors. So energy sector, for example, due to the population growth, to the consumption rising, the energy intensity, which is the energy that is used, the ratio of energy used per PIB. And of course, the observed impacts are extreme weather events, sea level rise, temperature and rise and warm days. And this is very important because, for example, in Algeria, we will see that we are in a very critical area, which will, where the impacts of climate change will be very important. And we see that in, for example, for some 800,000 years, that the current level of carbon dioxide level is very high. Now we are around 400 ppm. And so if this curve is going up, then it will be very dangerous for our planet because of the global warming. And also for temperature, we see that from 1880 to 2020, we see that there is an increase of nearly 1 degree. And of course, we hope that in 2100, we will stop this rising temperature to 2 degrees. Here we see, for example, from years 19 to 2016, if we see Algeria, we are here, in a very, so we are the first now. So we see Algeria here. So the temperature is under, variation is under 1 degree. But we see now the situation, we are in red, which means that in next years we will experience very hot temperatures. So we see here the 3 paths from 2000 to 2100. So we want, of course, to be less than 2 degrees. We want to use this green pathway. And of course, there is, if you use the national determined contribution of countries, then they will be insufficient to reduce this temperature. In fact, the indices are the commitments done in Paris Agreement, COP21. And if we do nothing, of course, so the situation will be very, very serious. And here you have this radiative forcing and the radiative balance, which are the balance between what the Earth is receiving, the heat received, and the heat which is emitted to the space. So we see, for example, here in these scenarios of the IPCC, that for 2100 here, only this green pathway or scenario here could make the temperature less than 2 or around 2 degrees. of in fact, the radiative forcing components here are, of course, the greenhouse gases, carbon dioxide, methane, ozone, and also you have the aerosols here and the albedo, which is the depending on the land use in, of course, in the area. I mean, if you have weight, for example, if it's green or white, if it's white, then you will have more reflection. Here also you have, for the whole planet, you have the business as usual in black here, and you have the global averages of temperature in land and in ocean. And you see, for example, that in Africa, we are going up here. So this is, of course, not good for. And this, of course, all these policies are depending on long-term low emission. Each country has to, in fact, communicate his LTLETs. For instance, for example, Algeria is a little bit late, so I think they will communicate at the end of the year this strategy about the energy mix and what are the sectors that will reduce this emissions, greenhouse gas emissions. So these LETs also, they aim to reduce greenhouse gas emissions, they increase the resilience of the impacts of climate change, and achieve social, economic, and environmental development goals with other tools that we can find in the Paris Agreement with the United Nations Fund for Climate Change here. So for the LETs or the strategies that have been communicated, for instance, so we have around 30 countries, and the first countries were Canada, Mexico, United States, and in Africa we had this Benin country that has communicated his strategy. So you will find, for example, what is the policy used by each country. For example, in Japan, they use smart technologies. Here in Africa, they use forestry management in order to reduce these emissions. You'll find the list just in this link. So each country, in fact, you see here some examples for United States, Canada, France, and you see what are their policies in order to reduce these emissions. For example, in United States, you have large-scale electrification of end users, for example, using electric cars. In Canada, in France also, you have, in fact, large-scale energy conservation. And of course, France is very particular because they use nuclear power. But most of them, in fact, are using new technologies and electrification in order to reduce their emissions. And you have of course, depending on the time you are beginning to reduce your emissions, if you are too late, for example, if we begin in 2025, then to reach the 2050 net zero emissions, then you what we call a carbon crunch. So it will be very, very difficult for you to reduce your emissions. So you have to begin as soon as possible in order to have this smooth curve. Of course, each country has his resources. For example, in Japan, even in 2030, we still find fossil fuels for 56%, gas, oil, coal, etc. And even in 2050, we still find this important share of fossil fuels. For example, if we see for the world here, 2050, we see that we will still have here oil and biofuels, coal here, and natural gas. Here you have the fossil fuels, of course, while the wind and solar will have a greater share, which means that between 2020 and 2040, this transition needs oil, needs gas, needs biofuels, etc. Here for gas, for example, we see that even in 2050, we still have the use of natural gas, which means that the transition, if we want to make a transition in Algeria, we need, in fact, the natural gas. But we will see that we need to reduce our consumption by energy efficiency and using renewable energy. Here also for coal, we know that coal is one of the most important pollutant we can find. So even in China, in the United States, we still have this power plants using coal. So if we want to make the energy transformation, in fact, we have to in buildings, transport, district heat, power, etc. So you have renewable energy, you have electrification of end users, and you have also the energy efficiency that could help us to drop from 33 gigatons in 2050 to nearly 10 gigatons in 2050. So this is one of the best scenarios. But the best scenario, in fact, is to change paradigm. In fact, we have to, when we think about future, to go from centralized plants to decentralized utilities. I mean, we must maybe leave this all this power plant because you have a lot of waste of energy. While when you are the producer and the consumer, so you are a prosumer, then it will be better for self-management of your energy consumption. So I come to the En-ROADS tool. This is from Climate Interactive. So you can go to the website, and so this is the first flow sheet you see. We can try to go to see the website. I hope yes. So here you get the beta version. You have to close it like this. And here you can use this, of course, this flow sheet. So here you have the share of different sources of energy, depending, in fact, on your policy. For example, if I don't want coal, I have just to put this lever here. And what happens? You can see that of course, the part of coal here is reducing, and also the temperature, the final temperature in 2100 is coming down. So I can use this in order to see what is the impact of reducing coal in this. And of course, you have here some menus where you can reset policies. You can reset assumption, for example. You can choose your graph. Instead of primary energy demand, for example, they can use electric energy capacity or total primary energy. Then you change I can see, for example, like I can put here the CO2 emissions with depending on the type of energy resource. And also you can choose the graph here, the graphs that you are using. For example, I can use the Kaya graph. Kaya is named after the Japanese. So you can maybe see more information here. I will make a demonstration at the end. So I will go back to my presentation. Yes, I continue with the presentation of the En-ROADS. In the En-ROADS, in fact, you have also equity consideration. It means that, for example, when you want to reduce any source of energy like coal is have a lot of pollution, but when you tax, you put a lot of carbon tax on coal, then you have low-income individuals that will suffer from this negative impacts. So you must take into account the social aspect, for example. And also, I said that En-ROADS is a multi-solving co-benefit. So when, in fact, you reduce, for example, the use of coal, then you have an impact on the health, on the ecosystem, etc. So in fact, the objective is to, when you use this tool with, for example, communities, or you have to reduce the temperature to lower than 2 degrees. When you are under 2 degrees, then it means that your energy mix is good. Because what does it mean? In fact, to have a 4-degree warming means that you have sea level rise. You can have the increase of frequency of drought across the globe, desertification, intense frequent heat waves and floods. That is what we are experiencing now. Committed warming, long-term equilibrium sea level rise, 13 to 15 meters, and maybe irreversible change. I see, for example, in New Orleans, we see this simulation, which shows what means to have 4 degrees. So you have the town of New Orleans here, city, which experienced many floods of the Mississippi here. So if you have 4 degrees of increasing of temperature, then you have all this area will be flooded. If I see, for example, here in New York, the Manhattan Island, you see all this area are flooded because of this. You see here, for example, in Wall Street, the bull, only his queue will be appearing in London, in Shanghai, and also you will have maybe a lot of costs due to fires, etc. Maybe 54 trillions by 2050, according to United Nations. I said also that is a multi-solving tool. It means that you have impacts on jobs, on food, on the resilience, on climate protection, energy, etc. So we can make some, and come back now to the, okay, to the beta version. We can see, for example, now you can play with the labels here. I mean, if you reduce coal, you have a small reduction. If you have a greater share of renewable energy, then you have maybe a small rise of temperature. So you see here, the temperature increased by 2100. If you have here the nuclear, it doesn't change. If I reduce oil, yeah, a little bit. Natural gas, nothing happens. Now, if you are going to a zero carbon policy, then just some degrees. Bioenergy, this is one of the topics that is important, because when the energy mixed, you will have renewable energy, you will have bioenergy, you will have hydrogen, etc. Now, one of the two, the silver bullets, if you want, will be carbon price. I mean, if I tax all this fossil resources, then you see that the reduction is very important. But the problem is, of course, if you tax, then I mean you will make people very poor because they don't have to pay all these taxes. And you have in transport, for example, energy efficiency, electrification of transport, and here of electrification in the buildings, energy efficiency. So what we can do now is we try to put this temperature increase less than 2 degrees. Okay. So for example, I choose to reduce here the coal. I can reduce a little bit oil. For natural gas in Algeria, I think we can use natural gas, even if methane here is responsible of some greenhouse gas emissions. So for the Canmore price, I put a small tax here. We can use bioenergy. We have a lot of research works, for example, in Nadrar, in Séduer, Bouzaria, for example, working on biodiesel, etc. I can, for example, have a share with highly subsidized renewable energy, so wind, PV, etc. Nuclear, yeah, maybe we could have some nuclear plant. And then I think we must have energy efficiency of our transportation system, because our cars, for example, are very inefficient. We don't have electric car, but we could maybe have by 2000 a small amount. In population, of course, we can keep it like this. We have statu quo, I think. And for the economic growth, of course, we need to develop the country. So we can put an economic growth, le taux de croissance, very medium economic growth. Of course, deforestation, we must reduce deforestation. We must also, in agriculture, for example, we must reduce methane and other gases. We must plant trees. And of course, one of the silver bullet also is technological, new technologies, which means that, for example, if I use, for example, methanization of dioxide carbon, I can make some hydrogen with the methane, for example. So by using technology, we can reduce greenhouse gases emissions. And in fact, when you go to the circular economy, we can use CO2 as a resource. In fact, so now if I use this technology, I can go down, let's say 1.5. So when I say this, so it's normally it's a good solution. Now, of course, you have to take into account your resources. And when you finish, then you can share, for example, your scenario here. And
Professor Kamal, your screen.
Yes, I'm finishing.
Your screen. No?
Is not
your screen. Not display.
Because I'm out of I am out
okay.
of. Okay, so I will go. I'll go out here. I will go out and. Yeah. So you will find, in fact, you can go to this website of Climate Interactive here, or you can go to this one and find all the tools, and you find also some videos. You can also attend a 7 days course in order to get a certificate from En-ROADS. And to finish with, in fact, all this energy transition must lead, in fact, to this super smart society using new technologies, using clean technologies, and that could manage our energy consumption model. And that's what you call Society 5.0. And thanks for your attention. So if you have some questions, I'm at your disposal. Thank you.
Professor Kamal, thank you for your presentations. If you have any question, you can ask.
Just to go out of the...
If you have any question?
So, of course,
if there is no question,
so
there is no question.
So, of course, En-ROADS is a decision tool in order to make some decision making, in order to try to get what energy mix up in Algeria in 2030, in 2050. And we know that, for example, the Ministry of Transition now is working on 1 megawatt or 1 gigawatt of solar energy. But we need, in fact, by 2030, to get something like 30% or 40% of renewable energy share. And that is nearly impossible if we don't put a lot of money and a lot of projects in order to get this the renewable energy share. Because, for instance, of course, except for PV technologies, renewable energy are very, very costly. But I hope that in maybe this year we will have this gigawatt of clean electricity. We know that, for instance, we have 400 megawatt from this power plants, PV power plants for example, in Jelfa or in Mghayar, Ain al-Malh, etc.
Another question, please. If you have another question, please.
You can ask the questions in French or in Arabic if you have problems.
Si vous avez des questions en arabe ou en français, vous pouvez les poser. Hein. Professeur Kamel, il y a une question. Quelle est la stratégie pour diminuer le CO2? Stratégie mondiale.
Oui, effectivement, il y a la stratégie mondiale, puis il y a la stratégie nationale. Donc, chaque pays, normalement, a communiqué en 2018-2019 la contribution nationale par le biais du ministère des Affaires étrangères. Donc, par exemple, l'Algérie, normalement, elle doit diminuer de 7% ses émissions. Maintenant, si elle a de l'aide extérieure, normalement, elle peut aller jusqu'à 20%. Donc, la stratégie, bien sûr, elle dépend de chaque pays. Par exemple, l'Algérie, c'est un pays qui est c'est un pays pétrolier, un pétrole plutôt gazier. Donc, nous avons intérêt à utiliser ce gaz pour faire notre transition. Le gaz est quand même une énergie, on va dire, relativement propre. Même si le méthane, bon, pose problème. Les fuites de méthane, que ce soit au niveau de la production ou de l'utilisation, le méthane a un pouvoir tel le réchauffement climatique, si vous voulez, le global warming potentiel, qui est plus important que le CO2. Donc, les stratégies, en fait, elles dépendent d'abord des budgets, elles dépendent de la sensibilisation des gens, et puis elles dépendent aussi de la technologie que vous mettez à la disposition sur le marché. Et puis, bien sûr, ça dépend de la recherche-développement dans les universités, les centres de recherche, parce qu'il faut de l'innovation. Actuellement, on est encore au début du développement des énergies renouvelables. Donc, si on veut prendre le train, comme disait le ministre de la Transition énergétique hier, ben, ça veut dire qu'il y a des trains à prendre qui mettent l'hydrogène. On est encore au début. Il y a des projets. Donc, Sonatrach, effectivement, qui met Exxon, Chevron, les compagnies pétrolières mondiales peuvent devenir des fournisseurs d'énergie au lieu bien sûr, de se reposer sur les hydrocarbures. Maintenant, les hydrocarbures, il faut les utiliser à autre chose, au lieu de les brûler comme on le fait. D'autant plus que nous gaspillons beaucoup d'énergie dans le bâtiment interne parce qu'il est mal isolé. Alors qu'on a des constructions avec les ressorts, etc., avec les matériaux naturels, effectivement, qui permettent de réduire ces émissions. En même temps, c'est esthétique, c'est bon pour la santé. Donc, il faut qu'on revoie l'efficacité énergétique dans les bâtiments. Il faut qu'on revoie les moyens de transport. Alors que là, vous avez la chance d'avoir un tramway. Le tramway, c'est une très bonne pour la ville. C'est une très bonne chose. Le problème maintenant, c'est les carburants en voiture, notamment le diesel, enfin tous les carburants fossiles. Il est temps aussi on parlait hier justement de l'importation de véhicules. Il est temps de passer à la voiture électrique. Donc on peut importer quelques voitures électriques, sachant que bien sûr la voiture électrique n'est pas une voiture propre à 100%. Il faut utiliser des énergies fossiles, des ressources, parce que nous voulons obtenir que les ressources. On parlait de la Perovskite tout à l'heure. Donc, c'est une ressource qui est très abondante. Ça veut dire que la voie de la Perovskite pour le PV, c'est une très bonne voie. Par contre, le cuivre, on sait que d'ici 2030, il va y avoir une pénurie. C'est pour ça qu'on est en train de parler d'économie circulaire. Comment réutiliser le cuivre, les rahots déjà qui existent dans les vieilles installations, etc. Mais sinon, globalement, donc l'Algérie est en train de travailler sur la stratégie de développement à long terme, donc bas carbone, à 2050. Donc, dans ces stratégies, en fait, d'après ce que j'ai vu sur le programme le ministère de la Transition énergétique, donc ce sont les énergies renouvelables qu'il faut développer. Et de ce côté, on avance. On était en avance, on avait des projets tels le Solar Paces les années 80, avec les centrales à concentration de Hassermel, le Mriyar avec du dessalement, le Biyad, etc. Malheureusement, ça n'a pas continué. Et le Maroc a pris, par exemple, le voisin marocain, maintenant il a pris le train et puis maintenant il nous dévance pratiquement. Les Égyptiens aussi, l'Égypte. Mais ce n'est pas trop tard, c'est-à-dire que donc il faut les énergies renouvelables, il faut une industrie des énergies renouvelables. Donc là, il faut de la collaboration, bien sûr, avec, apparemment, il y a 3 pays, donc l'Allemagne, la Chine et les États-Unis. Et deuxième chose aussi, c'est l'efficacité énergétique. Donc, on a construit beaucoup de logements. Malheureusement, ce sont des gouffres à énergie. Donc, il faut à tout prix isoler si on arrive à isoler les fenêtres, à faire un peu d'isolation, on peut réduire de 40-60% notre consommation d'énergie. Donc, on va réduire la consommation des hydrocarbures Tawana. Et ça, c'est un trésor pour les futures générations. Et donc, il y a trois triptyques, le transport, donc l'habitat, et puis les énergies renouvelables. Donc, c'est ce qu'ont fait tous les pays maintenant. Ils sont en train de parler d'électrification des end users. Donc, toutes les utilisations vont devenir électriques. Donc, la voiture, donc la cuisinière, par exemple, parce que ça, c'est un problème dans les pays africains, les pays d'Asie. Donc, faire en sorte que tout devient électrique. Et cette électricité, bien sûr, on doit la produire avec des ressources, des énergies propres. Donc, c'est un peu tout ça. Donc, pour l'instant, par exemple, l'Algérie n'a pas encore défini sa stratégie parce qu'elle doit la mettre sur le site de l'IPCC, qui est l'organe scientifique des Nations Unies pour les changements climatiques. Et donc, c'est dans cette. Quand vous lisez par exemple, pour les pays qui l'ont communiqué, il est disponible en PDF. Le Japon, c'est toutes les technologies intelligentes, c'est l'intelligence artificielle, c'est les énergies renouvelables. Donc, c'est ça qui va aider en fait à mieux gérer notre consommation d'énergie. Et on le voit. Pour terminer, par exemple, je vois l'exemple de Mazda City fait Dubaï ou l'a fait Abu Dhabi. C'est devenu l'exemple type. C'est une cité qui est à 100% énergie renouvelable. En même temps, la chambre, par exemple, la chambre des étudiants, dès qu'un étudiant consomme beaucoup, il y a un tableau de bord, donc il y a un monsieur énergie qui va venir taper à la porte pour dire attention, vous consommez trop d'énergie, il faut réduire. En même temps, la tour de Mazda City, il y a une espèce de phare ou de LED qui prend les couleurs rouge, vert, selon la consommation de la ville. Donc, quand ils vont voir la couleur rouge, le manara, donc ils vont automatiquement réduire leur consommation, d'eau, etc. Sinon, bien sûr, pour terminer, il faut que les gens soient sensibilisés, il faut qu'ils prennent conscience le modèle énergétique Tana, surtout en Algérie, il est à revoir. C'est-à-dire, c'est un modèle qui rejoint le modèle de consommation alimentaire, tel le gaspillage, tel le pain, en Ramadan par exemple, c'est le gaspillage de l'eau et le gaspillage de l'énergie. Donc ça, c'est des choses, donc c'est des triptyques qu'il faut, donc, qui doivent être intégrés dans notre stratégie 2030 ou la 2050, etc. Voilà, merci. C'est bon,
Professeur Kamal, il y a deux questions.
Ah.
Comment contribue l'université dans ce sujet?
D'abord pour non, je pense que l'université, je pense qu'elle est dedans, mais maintenant il lui faut des moyens. Je pense que les PNL, les projets, les appels à projets, etc. Il faut que les universitaires s'impliquent tout simplement, parce que c'est le nerf de la guerre, c'est l'argent. Hein. Je veux dire, moi j'ai vu par exemple toutes les universités algériennes ont des prototypes de production, par exemple, d'électricité, de chaleur avec l'énergie solaire. Mais pour l'instant, bien sûr, quand on vous donne un PNR à 300 millions, bien sûr, on vous donne la moitié. Ensuite, vous ne pouvez pas acheter ce que vous voulez. Donc là, il faut que ça change. Il faut rentrer dans des projets, s'il le faut, je sais pas, les projets PRIMA, les projets, par exemple, Union européenne, Union africaine, avec non seulement il y a de gros budgets, en plus il y a de la collaboration, parce qu'il y a des pays qui sont en avance. Là, moi, je sais que j'ai fait 2 projets européens avec, c'était l'Allemagne, enfin, qui prenait la coordination. Donc, on apprend beaucoup de choses. Après, bien sûr, il y a des outils, la banque, les douanes, c'est-à-dire si vous devez faire rentrer du matériel, il faut que ça soit facilité, il faut Sinon, bien sûr, l'université, je pense qu'il y a beaucoup de formations en énergie renouvelable qui ont été formées. Il y a des postes de doctorat qui ont fait les concours, les FATO. Bon, j'ai vu qu'il y avait beaucoup d'universités qui ont ouvert beaucoup de postes, hein, même si c'est peu. Et puis, il faut aussi qu'il y ait un chef d'orchestre. Chef d'orchestre, je pense, bien sûr, il y a la direction de la recherche, il y a le ministère de l'enseignement supérieur, mais là, de la coopération avec le ministère de l'Industrie, parce qu'il faut produire, nos équipements. Par exemple, dans ce sens, normalement, GTP, la zone industrielle de Raya à côté d'Alger, qui est une entreprise pétrolière, elle va produire le chauffe-eau solaire. Il y a un modèle chauffe-eau solaire qui a été adopté. Donc, le chauffe-eau solaire, c'est peut-être, dès qu'il y a ça va devenir une arme qui met le cas à bas coût. Un chauffe-eau solaire, bon, ça peut coûter, avec la subvention après, 40 000, 60 000 dinars. Elle va être peut-être imposée la conformité interne, le permis de construire. Donc, à ce moment-là, bon, on peut réduire les consommations pour le chauffage, pour l'électricité, peut-être de 30, 40, 50%. Ben, tout ça, c'est autant de gaz qu'on ne va pas consommer, qu'on va exporter ou qu'on va utiliser pour la pétrochimie. En fait, il faut que, si vous voulez, tous les secteurs travaillent ensemble. Avec l'université. Il faut que l'université, elle doit aller, les partenaires socio-économiques, il faut que notre recherche soit recanalisée vers la recherche utile. Avec, bien sûr, l'innovation, ce que font les startups peut-être. Et en même temps, votre produit que vous avez développé au sein de vos laboratoires, il faut qu'il soit doucement, je crois, commercialisable. Il trouve le marché. Et ne pas se limiter à des sujets, peut-être des sujets de doctorat ou des sujets de master, qui sont un peu généraux, là, qui s'intéressent à des thématiques dans les pays étrangers, par exemple. Il est temps de libérer il faut que l'université se libère, on lui donne les moyens. En même temps, bien sûr, il faut de la collaboration. Parce que, par exemple, la présentation de professeur Nasiruddin, par exemple, de l'EPFL, elle est excellente. Moi, je pense que c'est des choses qu'il faut... c'est à votre honneur, hein, l'université de Ouargla. Il faut refaire des choses comme ça, parce qu'on apprend... parce que c'est des gens qui sont en avance, qui sont eux-mêmes en collaboration avec des grands laboratoires. C'est des thématiques, c'est des enjeux très importants. Et avec juste une présentation comme ça, je suis sûr que tous les étudiants, les participants qui ont suivi, ça va leur donner des idées, ils vont apprendre peut-être, ça peut être un axe de recherche qu'ils vont développer, etc. Voilà, merci.
Professor Kamal, thank you very much for your presentation. We hope see you soon in Ouargla.
Inshallah.
I think that your family name is the same with my family name. I think that you are my cousin.
We are brothers.
Now, this session is Professor Kamal. This session has finished. Now we are going to pass to next session, presided by Dr. Ashuri Abdulrahim.
Assalamu alaikum. First of all, I would like to welcome all participants to this conference, wishing them an interesting follow-up. Without prolongation, we have two interventions. We can start with Dr. Boudin. Boudin, you are here?
Salam alaikum.
Alaikum salam.
Bon,
Welcome, Dr. Boudin.
Avant de commencer, donc Ramadan Karim, là, Inch'Allah, il faut donc, je vais vous présenter une petite conférence concernant la. Je ne sais pas si vous voyez la conférence ou non.
Non.
Donc, Dr. Ashon,
Yes.
est-ce que vous voyez la conférence? Est-ce qu'elle est sur
Pas encore, non. Université.
Mentoring.
You can continue. You can.
D'accord. Donc, je vais vous présenter une conférence concernant l'élaboration des nanocomposites polymères semi-conducteurs, puisque c'est un domaine où pas beaucoup de gens qui travaillent sur ce domaine. Donc, on trouve beaucoup de chercheurs qui font du sol gel.
Excuse me, Dr. Boudin.
Oui.
There is just the university me.
Mentoring.
Please share your screen.
There is,
Mentoring. University mentoring.
Please share your screen.
There is just university me. I can't see your presentation.
Okay. Now? No.
No.
Attendez, je vais le faire.
You can see?
Mais maintenant.
Maybe
No.
yes. No,
Huh?
yes.
Okay. But I have a problem with my PowerPoint. If I je préfère passer la conférence sous cette forme, donc sans passer, puisque j'ai un problème avec mon PowerPoint et je n'ai pas le temps de le régler. Sinon, on va perdre beaucoup de temps. D'accord? Donc, comme j'ai dit, c'est un domaine où il n'y a pas beaucoup de chercheurs qui travaillent sur ce domaine. Donc, je vais présenter cette conférence. Donc, je vais commencer par une petite introduction. Donc, puis, je parlerai sur les techniques expérimentales et sur les matériaux étudiés. Ensuite, je donnerai une petite analyse sur les résultats expérimentaux obtenus et enfin, je terminerai par une étude photocatalytique sur la dégradation d'un colorant qui est le colorant le plus connu, c'est le bleu de méthyle. Et enfin, je terminerai par une conclusion. Pourquoi les polymères nanocomposites? Donc, les polymères, en général, on a des polymères, des isolants et des polymères semi-conducteurs. Comme on va étudier des particules semi-conducteurs. Donc, on va utiliser des polymères isolants comme matrice haute. Donc, on va doper ces polymères par les nanoparticules de semi-conducteurs et étudier le nanocomposite ainsi formé. Donc, le polymère renforcé par ces nanoparticules présente des propriétés, de nouvelles propriétés physiques. Donc, il va combiner les propriétés du polymère avec ceux des nanoparticules semi-conducteurs. Ces nanocomposites à base de polymères trouvent beaucoup d'applications dans le domaine, physique ou médical, comme les tests antibactériens, donc le traitement et les thérapies de cancer. Donc, on peut utiliser ces nanocomposites dans le médical comme dans l'optoélectronique, dans la photocatalyse, l'électrocatalyse, dans l'environnement, dans la chimie, la pharmacie et beaucoup de domaines technologiques. En premier lieu, on va énumérer les problématiques qu'on doit résoudre. On a choisi de tester la photocatalyse par ces nanocomposites et l'étude, les tests antibactériens. Mais cette partie, je ne vais pas parler de cette partie, sinon on va prendre beaucoup de temps. L'objectif de ce travail, c'est de fabriquer et d'élaborer et de caractériser un polymère qui est le PVC, dopé par des nanoparticules de semi-conducteurs comme le sulfure de cadmium et l'oxyde de magnésium, et de tester la capacité de photocatalyse de ces nanocomposites sur le bleu de l'éthylène. Donc, le polyvinyl chloride, donc le PVC, c'est un polymère thermoplastique, donc c'est un polymère facile à produire donc, en utilisant un monomère de chloride de vinyle comme matière première, et son coût est très bas. Et on peut trouver ce polymère dans tout, c'est-à-dire il est utilisé dans plusieurs domaines dans notre vie. Par exemple, dans la plomberie, etc. Pour les matériaux utilisés, on a essayé d'élaborer des nanoparticules de cadmium, du sulfure de cadmium. Donc, le sulfure de cadmium, c'est un semi-conducteur à gap direct. Donc, il a un gap de 2,30 volts. Donc, il est non linéaire. Donc, il présente des propriétés optique non linéaire. Il est utilisé beaucoup dans l'optoélectronique, en particulier dans les cellules photovoltaïques, dans les détecteurs à gaz, dans dans plusieurs domaines. Il a une structure hexagonale, donc virgite, type virgite, donc de couleur jaune, et il est toxique. Donc son point de fusion, il est à 1480 degrés C. Pour le deuxième matériau, c'est l'oxyde de magnésium. L'oxyde de magnésium, c'est un semi-conducteur à large band gap. Donc, le EG est large. Il cristallise dans la structure cubique, donc type NaCl, donc c'est un cubique à face centrée. Donc, il est non toxique. La poudre est de couleur blanche. Donc, il est utilisé comme absorbant pour les agents chimiques toxiques. Il est utilisé dans la photocatalyse et comme réfractaire. Pour le CDS est préparé par voie hydrothermale. Donc, on mélange le CDNO3,2 avec le CH4N2S, donc à 100 degrés C. Après un certain temps, on obtient une poudre de couleur jaune. Cette poudre est séchée à 80 degrés C. Enfin, on aura une poudre de CDS. Pour le MG, on a utilisé la méthode Sol-Gel. Donc, on a préparé les nanoparticules d'oxyde de MgO par Sol-Gel. Donc, on a pris l'acétate de magnésium qu'on a dissous dans le 2-méthoxyéthanol, porté à une température de 60 degrés et sous oxydation thermique, sous oxydation magnétique pendant 2 heures. Après ce temps-là, donc, on fait un reflux de la poudre à 500 degrés C pendant 1 heure. Enfin, on aura notre poudre de MgO. Comme la photocatalyse pour le nanocomposite de PVC MgO, donc le MgO, on l'a dopé avec de l'argent pour faciliter ou augmenter le taux de photocatalyse. Donc, le dopage par l'argent s'est effectué lors de la préparation de la poudre de MgO, c'est-à-dire on mélange l'acétate, on dissout l'acétate de magnésium avec le nitrate d'argent dans le 2-méthoxyéthanol. Donc, et enfin, on aura une poudre de MgO dopée. Pour la synthèse du nanocomposite PVC, CDS et PVC AG MgO, MgO dopé à l'argent, donc, on a procédé par dopage ex situ. On sait qu'on peut doper les polymères lors de polymérisation du matériau, c'est-à-dire on fait la préparation du composite du nano semi-conducteur, nanoparticules du semi-conducteur en même temps que la polymérisation du PVC. Et une autre méthode, c'est de préparer à part les nanoparticules des sucres de cadmium et de l'oxyde de magnésium dopé à l'argent et de doper le polymère formé préalablement. Donc, on a adopté la méthode ex situ, c'est-à-dire on dissout le polymère, le PVC, dans le THF. On sait que les polymères ont beaucoup de solvants qui peuvent dissoudre ces polymères, tels que le THF, le chloroforme, pour certains le kérosène, l'hexane, le dichlorométhane, et ainsi de suite. Nous, on a adopté, on a choisi le THF. Donc, on a dissous 1 gramme de PVC dans le THF et on a dispersé les nanoparticules de CDS préparées par hydrothermale toujours dans le THF et on a ajouté un volume selon les rapports que je vais présenter tout à l'heure. Donc, la solution obtenue est transitée magnétiquement pendant une durée de 45 minutes et après, on laisse la solution au repos pour permettre au gros grain de descendre vers le bas de la fiole par pesanteur et aspirer uniquement à l'aide d'une seringue le liquide qui contient des particules de CDS de petite taille. Donc, et après, on dépose ces fibres sur des verres par la technique de spin coating. Donc, on aura des verres dont les films sont sur les verres. Donc, ici, c'est le PVC dopé MgO dopé à l'argent, et ça, c'est le PVC avec du CDS. Donc, les techniques de caractérisation qu'on a utilisées, donc, premièrement, on a essayé de voir structurellement est-ce qu'on a bien un composite ou un nanocomposite PVC, CDS, PVC, MgO dopé à l'argent. Puis, on a essayé d'étudier on a essayé de voir les propriétés optiques, donc par la mesure de la densité optique, parce que la spectroscopie est visible, et la photoluminescence. Et enfin, on a essayé de faire un test de photocatalyse. Donc, la première caractérisation qu'on a utilisée, c'est toujours l'étude au rayon X, de confirmer est-ce qu'il y a pénétration des nanoparticules de CDS ou non. Donc, comme on le voit sur la figure, c'est le PVC dopé à 1, pur 1%, 2%, 3%, 4% et 5% CDS. Donc, on voit bien que le PVC pur, donc la courbe noire, il n'y a pas de pic. C'est-à-dire que le PVC est amorphe. Et au fur et à mesure qu'on augmente le dopage, on remarque que les pics de CDS, donc les plans 100, 002 et 101, deviennent plus intenses. Donc, on voit bien que les positions angulaires des plans 100, 002 et 101, donc ce sont les positions 26,7, 26,9 et 28,3. Donc, c'est les 3 positions qu'on trouve. Bien sûr, il y a des shifts des positions angulaires. Ces shifts sont très petits. avec l'élargissement à mi-hauteur, donc en utilisant la fameuse formule de Scherrer, bien que la formule de Scherrer, donc, elle omit l'élargissement dû à l'appareillage. Donc, on a pu calculer les tailles des nanoparticules de CDS. Donc, ces tailles sont tous inférieures à 100 nanomètres. Donc les particules introduites dans le PVC sont des particules de taille nanométrique. Le même constat pour le MgO dopé à l'argent. Donc, on voit bien que au fur et à mesure que la concentration augmente, l'intensité des pics de MgO augmente avec l'apparition des pics de l'argent des plans correspondant au plan 220 et au plan 311. Donc, même constat, donc les tailles qu'on a estimées par la formule de Scherrer, ces tailles sont nanométriques. Donc, on a bien formé un nanocomposite PVC CDS et PVC MgO dopé à l'argent. On a essayé de faire des mesures d'infrarouge pour voir s'il y a comme les matériaux inorganiques, les bandes d'absorption ou de transmission infrarouge sont entre 50 et 500 nanomètres. On a essayé de faire les deux gammes. Donc, la première gamme, c'est entre 50 et 500 nanomètres pour révéler les bandes d'absorption du matériau du MgO, et la gamme entre 500 et 4000 pour essayer d'identifier les bandes relatives au PVC. La spectroscopie UV visible du nanocomposite PVC-CDS révèle qu'il y a un shift du bord d'absorption du CDS par rapport au cristal massif vers les grandes énergies, c'est-à-dire vers les petites longueurs d'onde. Ça implique bien que les particules de CDS introduites dans le PVC sont des particules de taille nanométrique. Pour la photoluminescence, on voit bien que non, ça c'est le calcul des gaps. La figure, c'est le calcul des gaps. Donc, la détermination des gaps. Donc, la même chose pour le MgO. Pour la photoluminescence, on a deux bandes. Une bande située dans l'ultraviolet, dans le proche ultraviolet. Cette bande est due à la transition bande à bande, et on a une autre bande située à autour de 550 nanomètres. Cette bande est due au défaut qui existe dans le gap du CDS. Pour l'étude morphologique, donc on a essayé de faire des schémas, des images MEP. Donc ces images MEP des PVC dopés aux nanoparticules de CDS. Donc ça c'est des grossissements de quelques dizaines de micromètres. Ça, c'est des grossissements de 100 nanomètres. On remarque bien que les nanoparticules occupent la surface des polymères. En général, c'est une surface qui présente des pores et que les nanoparticules occupent ces pores-là. Donc, on a centré sur l'un des pores et on voit bien que les nanoparticules s'agglomèrent pour former des grains de taille variable. Donc, il y a une dispersion de taille allant de 2 mètres jusqu'à une centaine de nanomètres. On a fait des images ASM. Ces images-là présentent, donc, on a fait le map pour le PVC dopé au CDS et pour le PVC dopé MgO, dopé à l'argent, on a fait uniquement l'ASM parce que c'était difficile de réaliser des images MEP. C'est difficile de réaliser des images MEP, donc on a préféré de faire des images ASM. Donc on voit bien que ces images, donc les surfaces présentent des rugosités différentes selon la concentration de MgO dans le PVC. Pour la photocatalyse, donc, on a préparé une concentration C0 de 10-5 mol par litre de bleu de méthyle et on a essayé de dégrader ce colorant. Donc, on a essayé de dégrader ce colorant par, ici c'est le PVC pur, ça c'est PVC 1%, PVC 5%. CDS. Donc, on voit bien que la dégradation, la courbe, on voit bien que elle diminue au fur et à mesure que le temps augmente. Donc, et cette diminution aussi, donc pour le même temps, donc on voit bien que il y a diminution en fonction de la concentration de CDS dans le PVC. Donc, on a tracé le logarithme de C0 sur C et on voit bien que il y a donc qu'il y a une diminution de la concentration en fonction du temps. Le même constat pour le PVC dopé, MgO dopé à l'argent. Donc, on remarque que ça, c'est la courbe pour le PVC pur, donc PVC dopé MgO et PVC dopé 10% argent, MgO dopé 10% argent. Donc, on remarque que l'argent augmente la dégradation du colorant. Donc, le dopage de MgO par l'argent augmente la dégradation du colorant. Donc, la même chose, on a ici tracé le logarithme de C0 sur C. Donc, on voit bien que les courbes sont mégawatts. Donc, et on remarque bien que qu'il y a diminution de la concentration au cours du temps. Donc, ça, c'est le mécanisme de la photocatalyse, c'est-à-dire les réactions qui se font. Donc, l'éclaircissement du nanocomposite par les ultraviolets permet aux électrons de passer de la bande de valence vers la bande de conduction. Comme il y a des impuretés dans le gap, donc cette paire électron-trou réagissent avec le trou réagit avec l'ion hydroxyle, donc pour dégrader le bleu de méthyle, et l'électron réagit avec l'oxygène, donc pour former le O2-, avec l'H, la H+, on aura enfin le H+, donc la dégradation. En conclusion, donc, on a pu fabriquer des nanocomposites CBS-PVC et PVC MgO dopé à l'argent. Le changement, bon, le spectre, le diagramme de rayons X ont confirmé la dispersion des nanoparticules dans la matrice du PVC. Donc, les images NEB ont montré une agglomération des nanoparticules CDS dans des pores à la surface du polymère. Donc, et on pense que la même chose, bien que qu'on n'a pas pu faire des images NEB, MgO, PVC MgO, et on pense que c'est le même constat qu'on aura si on a pu avoir des images claires de nanocomposites MgO, PVC dopé, MgO dopé à l'argent. Tous les films donc, sont transparents dans le domaine visible, donc ils présentent une forte absorption dans le domaine, dans la région de l'ultraviolet. Et on a remarqué qu'il y a un shift du bord d'absorption du CDS et du MgO vers les grandes énergies, c'est-à-dire vers les courtes longueurs d'onde. Ce shift est dû probablement à la petite taille, donc à la taille nanométrique, et du CDS et de l'MgO. Donc, on a aussi vu que les nanocomposites PVC, CDS et PVC MgO dopé à l'argent favorisent la dégradation des colorants, donc on peut les utiliser dans la purification de l'eau. Merci pour votre attention.
Dr. Boudin,
Oui.
thank you for your presentation. If you have any questions, Y a-t-il des questions? إذا كان هناك أسئلة من طرف المشاركين. Même dans les commentaires, il n'y a pas de questions. Donc, je vous remercie, Monsieur Boudin. On passe maintenant. Now we are going to pass to next presentation by Dr. Linda Isani. Dr. Linda Isani. Dr. Linda, you are here? You here, madam? Dr. Zabat? There isn't. Dr. Isani. Dr. Linda. Dr. Zabat.
شكرا.
ننتظر قليلا ربما يلتحقوا بنا دكتور عيساني او الدكتور زعباط.
شكرا.
اسمه شيء
ايش عندك النيميرو تاعو؟ وي شوف ها احمد هذا كتبت النيميرو تاعو غادي يحوس عليه. انا عندي ريونيون تا واش تنخطط غادي يحوس عليه. قلت انا 06 وريتو
هذا ما كانش
دكتور زبط. دكتور زبط. You hear دكتور زبط؟ دكتور زبط؟ دكتور زبط؟ Vous m'écoutez? Dr. Zabat, you are here? There is a problem. Dr. Zabat? Dr. Zabat? دكتور زبط لا يستمع إلينا لديه مشكل. Donc now we are going to pass to next presentation by now the next session isn't by Dr. Ben Mabrouk Lizhar. No. Dr. Zabat? Dr. Zabat? Dr. Zabat? No. We don't come to
pass to the next question. Zabat. Zabat.
Allô? Allô?
Oui.
Allô?
Zabat. Salam alaikum, monsieur Zabat. Monsieur Zabat. Est-il un problème? Zabat. Monsieur Zabat. Zabat. تسمعتينا monsieur Zabat? On voit votre présentation, mais il n'y a pas de son. Il n'y a pas de son. Monsieur Zabat. Vous m'écoutez, monsieur Zabat? Monsieur Zabat? Monsieur Zabat? Donc, we must going to pass the next session by Dr. Azhar Mbrok.
بسم الله الرحمن الرحيم. أعزائنا المشاركين في هذا المؤتمر الدولي، السلام عليكم ورمضان كريم. In the name of Allah, the gracious and merciful. طبعا نظرا لوجود خلل في أداء الدكتور البروفيسور زعباط، ممكن نأخر المحاضرة أو يتم إرسالها بشكل مسجل. في هذه الآونة، في هذه اللحظة سنقوم بعرض مداخلة الدكتور البروفيسور والعالم الكبير نضال بالسوم. على كل حال هو مش في التخصص تاع المؤتمر، لكنه يحب يقدم نصائح للطلبة والباحثين الجدد في مدة قصيرة. بدون إطالة نقوم بالعرض مداخلة البروفيسور نضال بالسوم. هي طبعا مهمة جدا خاصة للباحثين الجدد.
الادوات يجب يعني التحكم فيها او الاستفاده منها على الاقل. الآن هناك نقطتان مهمتان جدا، واعذروني إذا كانت يعني نقاط سلبية أريد إثارتها معكم من باب التحذير ومن باب توجيه خاصة الشباب، خاصة الذين لا يعرفون بعض النوع من هذه الأشياء. منها أولا مثلا النقل من مواقع أو النقل من أبحاث. هذه الآن صارت معروفة باللغة الإنجليزية بلفظ plagiarism، أو باللغة العربية الانتحال، أو أحيانا يقال السرقة الأدبية، يعني الإنسان يأخذ مثلا فقرة أو جمل أو أحيانا صفحات كاملة. يعني ياما مرت علينا حالات وجدنا شخصا نقل صفحات بالكامل، واليوم يعني لا يسمح بنقل جملة واحدة، فما بالكم بنقل فقرة أو بنقل صفحة من بحث آخر هكذا كما هو. حتى لو مثلا يستشهد الإنسان يقول ويقول فلان أو عن نقل عن فلان، لا يأخذ الإنسان صفحات كاملة، يعني ممكن يستشهد بفقرة ويعطي المرجع بشكل دقيق، ولكن حتى هذا كثيرا ما لا يحدث. ناس يأخذون، بل وجدنا في بعض الحالات أن الناس يسرقون أطروحة ماجستير وأطروحة دكتوراه بالكامل ويضع عليها اسمه ويقدمها على أنه هو الذي قام بهذا. هذه مسائل يعني إجرامية بدون مبالغة، هذه يحاسب عليها القانون، هذه الإنسان يشطب من قوائم الأكاديمية ولا يكون له مكان ولا يوظف في المستقبل بأي شكل من الأشكال إذا قام بهذا النوع من السرقة وبهذا النوع من الجريمة. ربما لا ينتبه الناس إلى شيئين: واحد، أن لدينا الآن أدوات، يعني مثلا في جامعتي أنا هنا لدينا أداة كل طالب يقدم أي ورقة في أي مقرر، تصوروا، ليس بحث علمي لينشر أو ينسب إلى صاحبه، ورقة. أنا طلبت من طلبتي مثلا يكتبوا أوراق في مواضيع معينة، عليهم أن يقدموا هذا عن طريق الإنترنت، عن طريق المنصة التي لدينا داخل الجامعة. وهذه المنصة مزودة ببرنامج، مثلا في برنامج اسمه سيف الساين، برنامج اسمه تيرنيتين، وبرامج أخرى، لتأخذ هذه الورقة قبل أن أفتحها أنا كأستاذ وأنظر فيها مباشرة، وتفحصها جملة جملة وتقول لي هذه الجملة أخذت من هذا المكان، هذه الجملة أخذت من هذا المكان، أو حتى أحيانا 80% 90% من هذه الجملة. قد لا تكون الجملة يعني حرفيا، ولكن معظم الجملة أو الفكرة كاملة أخذ من هذا المكان، وتعطيني تقرير كامل مباشر هكذا في دقائق أو أقل من دقائق، يطلع لي تقرير كامل مفصل عن هذه الورقة، هل أخذت وماذا أخذت ومن أي مكان إلى آخره. فهذه يجب الانتباه الإنسان أنه أي ورقة تقدمها على مؤتمر، تقدمها على مجلة للنشر، تقدمها على جامعة، تقدمها لأستاذ، تقدمها كمثلا جزء من أطروحة ماجستير، ورأينا هذا بالكثير، أطروحات دكتوراه إلى آخره، هذه الأوراق ستفحص جملة جملة. يجب أن يعرف الإنسان. هذا واحد. اثنين، أنه لدينا الآن الإمكانية أننا ننظر حتى في الأوراق التي تم تقديمها داخل الجامعة من قبل، لم تنشر، ولكن يعني مثلا أنا طلبة عندي قدموا لي أوراق الفصول الماضية وهي مخزنة الآن في السيستم. الآن إذا طالب آخر مثلا يقول أنا شاطر، عندي ورقة صديقي أو ابن عمي أخذ هذا المقرر السنة الماضية ويأخذ منها. فهذه يعني يجب أن ينتبه الإنسان كثيرا. ثم شيء آخر أنه يعتقد الناس، كثير من الطلبة يعتقدون أن ما هو منشور على الإنترنت وما دام هو منشور ومفتوح على الإنترنت ويمكن الوصول إليه مجانا ومفتوح كذا فيحق لي أن أنقل منه. هذا الكلام غير صحيح. كونه منشور مثلا في ويكيبيديا أو منشور في صفحة معينة إلى آخره لا يعني أن يحق للإنسان أن ينقله هكذا ويضعه في أطروحة ماجستير أو يضعه في ورقة أو في بحث أو في شيء من هذا النوع. الشيء الآخر الذي أريد الإشارة إليه أن ينتبه الإنسان، الباحثين خاصة والشباب المقبلين إلى آخره، وهي المجلات التي تستغل الباحثين. ما هي هذه المجلات؟ هناك الآن مئات ربما آلاف من المجلات منتشرة عبر العالم، بل هي التي تتصل بنا في كثير من الأحيان. أنا كل أسبوع أسبوعين بتجيني هكذا إيميل يقول لي ندعوك للنشر عندنا ونحن نعدك أن أي بحث تنشره لنا سوف نقبله في ظروف قياسية في وقت قياسي، أسبوع أسبوعين نعطيك موافقة. فطبعا الإنسان يقول إذا ورقتي راح تقبل بهذه السهولة وبهذه السرعة فأقدم لهم، لكن وربما يضيفون لك في الأخير أو بعد أن تقدمت بالورقة ووافقوا لك عليها يقولوا لك ولكن عندنا إحنا يعني رسوم يجب أن تدفع مثلا $100 $200 أحيانا تكون $500 تكون أكثر. فإن الإنسان يقول معليش أنا يكون عندي ورقة منشورة. وفي كثير من البلدان الآن حتى يتخرج الطالب مثلا بالدكتوراه يفرض عليه أن ينشر على الأقل ورقة ورقتين في مجلة دولية، فيقول هذه يعني توفي الغرض وخلاص انتهي من هذا الشرط فأنشر أنا في هذه المجلة. ولكن النشر في هذه المجلة هو كارثة أكاديمية علمية ليست لها أدنى قيمة، بل تسجل وصمة في جبين هذا الباحث أنه نشر في هذه المجلات التي هي مجلات استغلال ليست لها أي قيمة علمية ولا تضيف شيئا في سيرتك الذاتية في السي في ولا يصح الإنسان أن يتعامل معها. المهم أردت أن أعطي بعض النصائح هكذا، ربما بعض منها تكون مفاجئة وتكون هكذا صادمة إلى حد ما، ولكن في كل الأحوال أنا أقول هذا لأنني أريد أن أشجع الشباب والباحثين المقبلين على المجال الأكاديمي والمجال البحثي، وأهنئكم على تنظيم هذا النوع من المؤتمرات، وإن شاء الله يكون لنا تواصل في المستقبل بالتوفيق إن شاء الله. السلام عليكم ورحمة الله.
طبعا نشكر البروفيسور ميلاد السوم على النصائح القيمة وعلى قبوله الدعوة رغم الظروف ورغم الظروف الصحية. ونتمنى إن شاء الله تكون يعني هذه النصائح وصلت لجميع الباحثين طبعا، وهي طبعا على مستوى الجزائر. طبعا هناك طبعا دوريا هناك قوائم للمجلات المفترسة والمجلات الغير طبعا مصنفة، وفي المقابل هناك كذلك مجلات طبعا مصنفة وذات قيمة كبيرة وعالية اللي هي طبعا مهمة. بل طبعا نختم نشوف هل في الكلمة للدكتور عاشوري عبد الرحيم يحاول يتواصل مع البروفيسور الزعباط.
نعود من جديد. السلام عليكم ورحمة الله وبركاته. هل الأستاذ زعباط معنا؟ أستاذ زعباط؟ دكتور زعباط؟ يا دكتور؟ دكتور زعباط؟ دكتور زعباط؟ دونك بتاتر تكون ربما تكون هذه آخر محاولة مع الأستاذ زعباط من جامعة قسنطينة. دونك الآن أحيل الكلمة للرئيس رئيس المؤتمر الدكتور الأزهر محمدي لاختتام هذه الجلسة. السلام عليكم ورحمة الله وبركاته.
الرحمن الرحيم. بدوري أنا أشكر جميع المشاركين في هذا الملتقى في هذه السيسيون invited speakers. أعلن فقط أنه هناك دي سيسيون أورال خاصة بكل توبكس، بمعنى أنه كل أستاذ مسؤول بالتوبكس قد حدد وقت لمناقشة المداخلات الشفوية representation. مدة المناقشات هي حددت بساعة. في الأخير تاني أشكر جميع المشاركين واللي راهم معنا في لاسيسيون هذه، وبالتوفيق للجميع.